So a couple things before we get started. Normally, this, of course, is a face-to-face class, and what I mentioned on the first day is that I'm going to do a few sessions through the web until the COVID situation in Hamilton County turns around a little bit. I checked, it's looking better. I think the hospitalizations are going down, but I think we're still in the purple. I think the infections are going up. I'm keeping an eye on that. Good news is my mom, who I take care of, as I mentioned, she's almost 80. She goes tomorrow to get the first part of her vaccine. So as far as when we're going to meet face to face, just I know a couple people sent me a text to ask about it. Just kind of keep in touch with me, and I'll make a post. I'll let you know if we're going to meet next week face to face or not. As far as assignments due, well, normally we would meet tonight, and whatever I assigned last week would be due tonight. And what would have been due tonight would be the first lab. There was a Tesla assignment, and then there was a homework assignment. Well, the lab, I'm going to give you a couple weeks to do lab one because it's kind of calculation intensive. You need to spend a little time on that. So normally I give students 2 weeks to do that. So that's not due tonight. The Tesla assignment would have been due tonight, but since we're not meeting tonight, I did extend the due date until this Sunday. So Sunday at midnight, or actually before midnight, you want to go ahead and submit that assignment. I think a couple people already submitted it to Blackboard already. There is a link in the week one folder. You can click on that link, attach your file, and upload it. I prefer if you upload it as a PDF. I think it opens up a little bit easier in Blackboard. If I have any issues or trouble getting it, I'll let you know. So there's nothing due tonight other than what would have been due. It's a Tesla assignment. Excuse me. But since we're not meeting tonight, I did extend that until Sunday. So the other thing that we would do if you were coming in is we would have a quiz. We would do a quiz first thing before we start the lecture. And again, since we are not coming in tonight, you won't have a quiz tonight. I thought about giving you one that you can upload here on Blackboard, but I decided that what I would do is I'd ask for that quiz. I'll post something over the weekend that you can take the quiz over the weekend, and we'll make it due, and you can submit quiz to that way. So I don't know what it'll be right now, but depends. We'll see how far we get in the topic. Michael, you have a question? Michael? Okay, I guess he. All right. Well, let me share a document with you. What I want to do is just kind of briefly go over, and I mean very briefly go over what we talked about last week, and then we need to continue. We're still on week one material, but week one material is a lot there. So I'm sharing a document with you right now. And last week when we started the course, I asked the question, what is DC and what is AC? What's the difference between DC and AC? And somebody said, well, DC is direct current, AC is alternating current, which is correct. And then I said, all right, well, what does it mean to have direct current? If I have direct current in the circuit, that means that the current flows in one direction and the magnitude of that current does not change. Whereas alternating current, the current starts out at 0, builds up to a maximum amount, and then goes back to 0. And while it's doing that, it also changes direction. So it starts out 0, goes up to a max value, goes down to 0, and then reverses direction, alternates back and forth. One of the important things I had you do last week, I had you watch a video. I had you watch a video on Faraday's Law, because everything we're going to talk about this semester actually starts and is based on Faraday's Law. So Faraday's Law, there was a video, and you watched the gentleman in the video basically demonstrate Faraday's Law. And remember, Faraday's Law says that if you want to induce or create a voltage, using Faraday's law, all you need is three things. You got to have a conductor, and usually we form that conductor in the shape of a coil. So you need a coil, you need a magnetic field, and then there needs to be relative motion between the magnetic field and the coil. So I can have the coil stationary and move the magnet, or I can move I can have the magnet stationary and move the coil. There just has to be relative motion between the two. And if you do that, he demonstrated in the video, or Faraday says that you can induce or create a voltage. Now, what is voltage? Well, we learned in DC that voltage is nothing more than the separation of charge. If I take charge and I separate it, I have an electrical potential difference, and that electrical potential difference is called voltage. And so batteries separate charge. When you took DC, we used batteries in DC to separate charge, to give us voltage. In AC, now we use principles based on Faraday's law. We use those forces, those electromagnetic forces that we went over last week to separate charges to make a voltage. Now we make that voltage with a rotating machine, and that voltage turns out to be an alternating voltage, which then produces an alternating current. So everything we do now is based on the fact that we can create voltage now. We can separate charge, not just with the battery. We can do it now with the rotating machine, and we call that rotating machine a generator. As a matter of fact, we call Faraday's law generator action. And so I spent the majority of the time in the last class trying to explain, to kind of build a generator on the board and to explain how the generator works and why that generator must produce an alternating waveform that looks like a sine wave. I also mentioned the fact that in AC, there's really three different kind of alternating current waveforms. There's one that looks like a sine wave. There's one that looks like a square wave. There's one that looks like a triangle wave or sawtooth. And so in this class, we actually deal with all three. But when we say AC, the main one of those three we're talking about sinusoidal AC. So if I say AC, by definition or by default, I mean sinusoidal AC. If I mean a triangle wave or square wave, I got to tell you that. So in this class, AC means sinusoidal AC. And so as I continued in the discussion last class, I asked the next big question. Okay, we got an understanding of AC and DC. We know the difference between the two. But the next question was, why do we need both? Why do we need both AC and DC? And so we went through, and I reminded you of an equation on the board. That equation showed the resistance of wire. And we talked about this in DC, that the resistance of wire is directly related to the length of the wire. The resistance of wire is directly proportional to the length of wire. So the longer the wire, the more resistance in that wire. And that presents a problem when we're trying to send electrical energy from one place to another. I mentioned the fact that Thomas Edison, in the early part of the last century, had the country wired up, and he used the DC system. And there were great power losses because there were great distances of wire that current had to move through. And so there were great power losses in the wire. And then entered Nikola Tesla. Tesla, by all rights, is called the father of AC. The father of AC. And I went through and I talked about a device which we don't really know how it works yet, but we'll get into it. The device is called a transformer. A transformer takes an AC voltage, and it can take that voltage and make it bigger, or it can take that voltage and make it smaller. If the voltage gets bigger, we call that transformer a step-up transformer. If the voltage gets smaller, we call it a step-down transformer. When we step up the voltage, the current has to drop. And so what we can do is, and this is what you're looking at on your screen right now, this is an example of a power distribution system, basically which Tesla is responsible for, more or less. And you see here that we have, in the picture in the upper left-hand corner, we have a hydroelectric dam. Water falls over the dam and spins the turbines. If you remember, one part of Faraday's law says that you have to have motion. You got to have something moving. Either you got to move the magnet or the coil. So what we can do is we can let water fall over a dam. The falling water turns a turbine, and the turbine can spin the coil, or that turbine can spin the magnet. The turbine is what gives us the motion. And we can use that to create generator action. And I guess in this case, the diagram that you're looking at, that would be considered clean energy. We're not burning anything to produce electricity. Now, when you use hydroelectric power, when you dam up water, that has its own problems. So don't think you're getting away with anything. It might be clean energy, but when you dam up water like this, depending on where you dam the water up, it can cause damage also. But that's not what this class is about. The point I'm making is, though, you can see in the diagram that after the generator, the voltage actually is stepped up, and about right here, stepped up to 500,000 volts, 500,000 volts. And so we send the voltage out at a high voltage, which means the current is low. We transmit power in the form of high voltage, low current. If the current is low, since power loss is equal to I squared R, power loss is the current squared times the resistance of the wire. If I lower the current, then I greatly lower the power loss in the wire. So what we can do here with AC that we cannot do with DC is we can step AC up to a really high voltage. We can send that power out as a high voltage, low current. When we get that power or energy where we need it, we can go through step down transformers, and you see that here that we go down from 500 kVs to down here we're at 66 kV, and then 4.8 kV, and eventually we get to your house. We step it all the way down to 240 volt two phase. We split those two phases off, and then your house, you can have 240 two phase, maybe in your basement to run a dryer. Or you can have 120 single phase, and that's what when you plug something into the wall, that's what you're using. So the answer to the question, why do we need AC? Because AC is really, really, really good, a really, really efficient way of moving energy back and forth over electric wires. All right, well, that makes sense. Why not make everything AC then? Forget about DC. Let's keep it simple. Why not make everything AC? Why not make your cell phone AC? Why not make everything AC? Well, that's not a good thing either, because typically, if I have all things equal, if I'm going to design two electrical systems, often it's a lot easier to design a DC system than an AC system. I mean, if you think about it, we made your phone AC, your battery by definition can only put out DC. How would you have any cordless devices? So we really have to have DC. Life's a lot simpler for DC. So in the world we live in, here's how it works. For the most, we generate electrical power in the form of AC. We distribute that power in the form of AC. And then when we get the power back where we need it, or we get it to where we need it, there's a device or circuit called a rectifier that changes that AC to DC, and then we can use our devices. So even though you plug in certain devices like your TV or your microwave oven or maybe your cell phone, these devices look like AC devices, but in reality, say a personal computer, you plug it into 120 volts AC, but there are circuits and devices inside the computer or device that converts that AC to DC. So most of the devices you use in your everyday life, most devices are in fact DC. Not all, but most or many of the devices are DC, and that's AC that's been converted over to DC. And so that was this first diagram. And then we tried to drill down a little bit deeper in our conversation last week. I said, all right, we're going to build a generator. I want to understand how this generator actually works, and the generator works, and what kind of waveform this generator produces. And so without going into the details of what we talked about, and by the way, the video of that discussion, if you missed it or you need to rewatch it, it is on Blackboard and YouTube. So you can always find these videos as long as we're meeting over the web. I will record the lecture, and you'll have access to that. You can go to either YouTube or you can go to the past lecture folder, click on the link, the date that you missed, and you'll have it. Now, when we start meeting face-to-face, I probably won't record these lectures, but I do have other pre-recorded lectures that you may be able to use if you miss a class or you need to review materials. So just keep that in mind. So we went over this generator, and we introduced the concept of the right-hand rule, and we used the right-hand rule to explain how if voltage is a separation of charge and the generator produces voltages, how does the generator separate charge to produce a voltage? So we went through that, and basically we applied the right-hand rule to a wire cutting through a magnetic field, and we were able to see the direction of the force on the charges in that wire, which basically indicated the direction, polarity of the voltage across the wire. And we were able to see that as that wire moves back and forth, that by definition, that voltage had to be an alternating voltage. And if the machine is producing an alternating voltage, then it has to produce an alternating current. An alternating voltage will produce an alternating current. And so we went through and we talked about Faraday's law, and we applied it to the generator. And this diagram here, and I don't know if I did a very good job, explaining this. It's a lot easier to do face to face, but when I'm talking and I'm talking into the camera, looking at this thing on the web, I don't know if I was effective. But again, hopefully you have a general idea of what's going on here. The point of this picture is that as we go around, as we move that generator coil around in the magnetic field, at certain points it's not cutting through any magnetic field, and then at other points it's cutting through a maximum amount of magnetic field, and at other points the conductors circulating around the magnetic field are changing direction. The whole point of this diagram and the one below it is that if you follow the coil around 360 degrees, and what you get are forces that are sinusoidal, which produces a voltage that's sinusoidal, which means that the current produced by a rotating machine or generator has to be a sine wave. And so this document you're viewing now kind of walks you through that. As you start off with that generator coil at 0 degrees, and you move around, as that generator coil moves around through 90 degrees, over the 180, all the way around to 360, it's tracing out basically a sine wave over time. And so this is what the AC voltage or AC current, this is the way we represent it. We represent it as a sine wave because all rotating machines, all generators, produce sinusoidal AC voltage, which then produces a sinusoidal AC current. And so we went through a whole lot of talking last time, and that's kind of where we ended up. So I kind of want to pick up where we left off, and we're going to, now tonight, we're going to learn about some different forms of AC, not different forms of AC, but different ways we can think about AC, and we're gonna look at some equations and quantities that will help us to solve some AC problems. So I want to put the generator back on the board. Now, I would highly advise guys take good notes because there's a lot of there'll be a lot of pieces to this. I think the end result, whether you understand everything I'm going to talk about or not, the end result, I think everybody will understand it. But I'm speaking mainly to the people that can kind of follow along with me and kind of see where things come from. If you can't, the rest of the course is not based on understanding every little detail I'm going to talk about. But in the end, when I end up with the final representation of an AC waveform, you do have to know everything about that. And so I'll start like this. If I want to build a generator, you already know from our discussion last time, they got to have some magnets and they got to have a coil. And that coil has to rotate in the magnetic field. How we rotate it just depends. I mean, I could put a shaft right here. I can put a wheel on the end of that shaft. I can put a belt around that wheel, and that belt can spin it. That's the way your car generator works. There's a serpentine belt that spins the generator. Or maybe I put some blades, some fan blades on here, and I can stick this up in the air and the wind can blow and turn it. Or maybe I put these blades under a waterfall. The falling water turns the coil. Some kind of way I got to spin this, because Faraday says if I want to produce or induce voltage, AC voltage, I got to have a coil. I got that. I got to have a magnetic field. I got that. And that coil has to move through the magnetic field. So that's what we're talking about. How do we move the coil? So that's an easy thing to do. We can move the coil, and depending on where you're located, your power company has different ways of moving that coil. I think here in Hamilton County, Duke Energy, they actually burn coal, which heats water, and the water makes steam, and the steam shoots up, and the moving steam actually turns the turbine. Not a very clean way of producing energy, but it's the way it's done around here. There are other ways to do it. But the point is, we get this thing rotating. So this is a physical machine, and what I would like to do is kind of get away from this and kind of abstract away from the physical machine, so we can come up with some equations to represent what we're dealing with. And the way we do that is, I'm gonna on this coil, I'm gonna place an arrow. I'm gonna take an arrow and fix it to this coil. You might think, okay, well, why are we doing that? Well, the reason we're doing that is, as this coil turns to generate electricity, the arrow is going to spin. And if I allow the arrow to spin, then what I can do, instead of actually worrying about the actual generator, I can come over here off to the side, and I can make an axis, an XY axis. And what I can do is, I want to keep track of the generator as it spins around. And the reason I want to do that is because as it spins around, go back to this. The reason I want to keep track of that generator is because as it spins around, it's actually producing forces that produces a voltage that looks like this. It looks like a sine wave. So I want to follow kind of the coil around 360 degrees as it produces the sine wave. You can see here in the picture, let me get up. Right here, that arrow, which is what I'm attempting to draw on the board, is at 0 degrees. It's moving this way. It's moving counterclockwise. And as it moves counterclockwise, it produces a voltage. And you can see in the next diagram that as this arrow now starts to rise up a little bit, maybe it might be at, I'm guessing, a little bit, maybe 50, 60 degrees, they're starting to produce a voltage. And you can see here at 90 degrees, that coil, when that coil is at 90 degrees, it produces the maximum voltage. And then it starts to go back to 180 degrees, so the voltage it produces is going to fall down to where that thing is at pointing directly at 180, then it's not producing any voltage. It's not producing any voltage at 180 degrees because it's not cutting through any magnetic field. At 0 and 180, we're not cutting through any magnetic field. Let me go to this other picture so you can see. When that coil is at 0, this is at 0 degrees, you're not cutting any magnetic field. Faraday says that coil has to cut through magnetic field to produce voltage. And when you're at 0 degrees, or when you have one at 180 degrees, it's not cutting through any magnetic flux. So therefore, it can't produce any voltage. It's only when this thing comes up away from 0 degrees and start to move towards 90, then it's cutting more and more and more flux, which means it's producing more and more and more voltage. Until we get to 90 degrees, and they're trying to exaggerate it in this diagram. See how they have the magnetic waves kind of bent? They're trying to show you that you're cutting through way more flux right here than you are here or in the first diagram. So you're going to cut through the most flux at 90 degrees, which means you're going to produce the most voltage at 90 degrees, which means you're going to produce the most current at 90 degrees. But when you go away from 90 over to towards 180, then the voltage is going to drop back down towards 0 until you get to 180, and then it's going to be at 0 again, and this process repeats. So what you're looking at now in this diagram, you're looking at one complete revolution of the coil as it rotates around from 0 degrees to 360 degrees in that magnetic field. You're looking at a representation of the voltage or current produced by that coil as it rotates from 0 to 360. So one time around basically gives you one of these right here. It gives you one sine wave. So that's kind of what I want to talk about. Well, to do that, just like in the diagram, they took an arrow and they fixed it to the coil, and now as that arrow rotates, then I can actually put the arrow right here, and I can follow that arrow as it rotates. Now, I want to talk a little bit about that arrow, and this is the point where if you're not writing anything down, you really want to write down what I'm going to say next. So make sure you're taking notes. The arrow I have fixed to the coil actually has a name. It's not really the arrow, but it's the representation of that arrow that I have over here. When you take an arrow and you fix it to the origin of a Cartesian coordinate system, this is a smart people way of saying axis, and you let that thing rotate, then that arrow is called a phasor. A phasor. You might have heard of vectors. I think I asked this question to you guys. Probably some of you heard of vector quantities. You know, in physics, if you have a physics course or some other math course, you talk about scalars, you talk about vectors. Now, if what I'm saying you don't know about, it's okay, you'll be all right. But if you did in math or other courses, you study vectors, you know that there's two quantities that you deal with a lot in physics: scalar quantities and vector quantities. A scalar is any quantity that just can be represented by just a number, like temperature. A vector is any quantity that needs both a number or magnitude and direction to specify that quantity. That's a vector. Well, there's actually another quantity called a phasor. And all the phasor is a vector or arrow whose tail is fixed at the origin of a coordinate system, like I have right here. And that vector rotates. Now, let me grab my prop, my pen. Hopefully I got my pen. I can use this as an arrow. Hold on a second. All right. So imagine this is my vector. So a vector is just an arrow. And the way you specify a vector is by its length and its direction. So if I have a force of, let's say, 10 pounds, force happens to be a vector. So I can make that 10 units long, or I can scale it down if I wanted to. But I can make 10 units long to represent 10 pounds of force. Then I got to specify the direction. The direction could be like that, or like it could be any direction. If I have a vector and I change the direction or I change the length, it is a different vector. If I take that vector, now the length doesn't change anymore, and I fix the tail of the vector on the coordinate system like this, and I let it rotate. Now we call that vector a phasor. So many of you probably heard of vectors. I don't know how many of you have heard of phasors. A phasor is a vector whose tail is fixed to the origin of a coordinate system, a Cartesian coordinate system, and then we allow that vector to rotate. That's a phasor. The big difference is this, that a vector, once I have a vector and I specify and set its length and its direction, I can move that vector anywhere I want to in the entire universe, and it's the same vector. Moving the vector around doesn't change it. As long as I don't tilt it or make it longer or shorter, it's the same vector. So vectors I can vary in position, whereas phasors vary in time. Vectors vary in position, phasors vary in time. And again, if you can't wrap your mind around that, it's not a big deal. But for those of you who can see what I'm saying, it's kind of cool. Here's the point, that when I take that vector and I fix it to a coordinate system and let it rotate, this vector is telling me where this coil is in the magnetic field. When this coil is flat like this, I'm going to draw the phasor like that. As it moves around in the magnetic field, as it moves around, this vector or that phasor is going to follow it around 360 degrees. And so basically this is telling me the position of this in this journey around and around and around in that magnetic field. So the term phasor. It's a rotating vector that varies in time. Now, in the picture here, and I'll go back to this picture briefly. In the picture here that we referred to before, this one, they're showing you this rotating vector right here. They're showing you the rotating vector. And the way they get this sine wave, and I want to talk briefly about the way they get the sine wave, they start the vector off right here at 0 degrees. So it's right here. And they let this vector rotate. Now this vector, or phasor is a better word for it. Phasors can rotate any direction you want, but by definition, we typically let a phasor rotate, when we talk about it, in the counterclockwise direction. So you'll always see me rotating the phasor in the counterclockwise direction, which is that way. There's no law that says we have to do that, but it's just by convention, that's the way we choose to do it. So we attach our phasor to the origin of the axis and we let it rotate. Now don't forget what the phasor is doing. The phasor is telling us where this coil is as it moves around 360 degrees in that magnetic field. It's telling us where the coil is. And so the way they get that sine wave picture is this. Imagine you have a light. Imagine you have light shining this way on this phasor as it rotates around. And then imagine you have a screen, like a movie screen, like that. And what you're looking at is, as this phasor moves around 360 degrees, you want to look at the projection of the shadow on the screen. And if you look at the shadow on the screen, when the phasor is at 0 degrees, which means the coil is at 0 degrees, then what you will see on the screen is just the reflection, which is a dot. You see a dot. Now, what the shadow is representing is the magnitude of the forces that separate the charges. And since the voltage produced by that separation of charge is proportional to the force that's causing separation, you're really looking at basically how the voltage is created. So however the force is acting is how the voltage is acting. And by acting, I mean, since the force is a sinusoidal force, then the voltage produced by that force is also sinusoidal. That's why we get a voltage sine wave, because the force that produces the voltage is a sine wave. So as we move around this way with the phasor, and I look at the shadow, say in this position, the shadow now is like this. And so I draw the shadow up like this. When I come to this position, the shadow is going a little higher. So I make it a little higher. Well, when I get to 90 degrees, when that phasor or coil is at 90 degrees, the shadow and the phasor are exactly the same height. So that's my greatest value. It's the same height. And then when I go over here, remember this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. Well, now when this coil or phasor comes over to quadrant 2, well, now I got to move my light source over here and put my screen up this way to look at that shadow. But when I move it over here, you can see as it moves from 90 degrees to 180, now that shadow is getting smaller and smaller and smaller. So it starts to decrease until I get to 180 and I'm back at a dot. I think I'm running out of picture in my in the camera frame. I'm probably running out of room. But basically you can see what's going to happen as I go around through 360 degrees, then the shape that this thing is producing, and this is only 1/2 of it. I'm getting that, so I got this, as it went from 0 to 180, and then when it gets over here in quadrant 3 and quadrant 4, it's making the other half of the sine wave. So every time I go around with the generator coil, it goes from 0 volts to some maximum voltage, back to 0 volts, and then when I get down from 180, 270, back to 360, it starts to increase again, but the fact that the sine waves, the bottom part of the sine wave is now below the axis, what that indicates about the voltage, it means the polarity of the voltage has changed, which means the direction of the current has changed. So every time that generator coil goes around one time, it produces a voltage like this. And if it keeps going around, just free running, it's going to produce a continuous sine wave of voltage like this, which is going to produce a continuous current that we call alternating current that looks exactly like that, like a sine wave. So the question is, okay, you may or may not understand all or some of what I'm saying, but the question is, how do I describe that voltage mathematically? How do I write the equation that's going to tell me what that AC voltage looks like? And this is where we want to get the math into this stuff that we're talking about. So here's how we're going to do it. It's kind of nice that nature, when we use Faraday's law in this fashion to produce a rotating machine, it's kind of nice that the voltage produces a sine wave. And the reason it's nice is we already know what that looks like mathematically. We already know that if I have a sine wave, that sine wave can be described like this. So if you had your algebra in trig class, you studied the sine function, the cosine function, tangent function. You know, there's the other three, the cotangent, the secant. You look at all of that. I'm talking about the sine function. And the sine function is what we call a periodic function. Periodic function. What does it mean to say I have a periodic function? Well, the key is the subword period. That means that this sine wave is going to keep repeating itself over and over and over again. So here's what I mean by that. If I make a sine wave, here's one sine wave, and if I keep generating a sine wave, it's just this wave over and over again. So it repeats at a regular time. This time right here, if this axis right here is time, and this is voltage, and this sine wave starts here, goes up to a maximum value, goes to 0, goes to a maximum value in the negative direction, and goes back to 0, and at this point right here starts to repeat. So the time from here to here, that time is called the period. And the period is how often that sine wave repeats itself. And so if you're taking notes, what you should do, that's one thing I want you to write down, the period. The period is how it takes the sine wave to repeat itself. How much time, T-I-M-E, how much time does it take the sine wave to repeat itself? That's called the period. And since the sine wave is a waveform that repeats itself, we say that this sine wave is periodic. Sine waves and cosine waves are periodic. So the period is one important term. Now there's homework 1 on Blackboard already, which would have been due tonight, but since I didn't get through the lecture, I couldn't make the homework due. Well, what we're doing right now, the stuff you should be able to do those problems after tonight. You'll know enough to be able to do homework 1. So next time you can turn homework 1 in because you'll be able to do the problems. So our first AC term that we're going to use is the term period. And period means it's the time it takes to produce one cycle of the waveform. How long does it take for the sine wave to start to repeat? And remember that really this sine wave, one cycle of the sine wave is produced by the generator coil going around one time. If I took the generator and turned it one time, it'll make one of these. Well, most generators spin constantly, so they're going to continue making these waveforms of voltage or current. Okay, well, the point I was making is the mathematicians already know how to write an equation for the sine wave. It's this. And I don't know how long ago you guys had trig, but can anybody tell me the maximum value of a sine wave? Anybody remember? What's the maximum value of a sine wave?
1.
1. I think that was Jacob, or somebody said 1. So what do you mean the maximum value? Well, see, this is a function, right? Here's my independent variable, theta, and here's my dependent variable. You put whatever you want in there, whatever number you want. If your calculator is in degrees, you can put in whatever degrees you want, 0 degrees, 100 degrees, 1,000,000,000,000 degrees. I don't care what you put in there for the independent variable. The highest a sine wave is ever going to get is 1, and the lowest it's ever going to get is -1. So a pure sine wave, all it does is this. A pure sine wave, all it does is vary between 1 and -1. So it varies. And keeps going. And as long as that machine is rotating, making the sine wave, it's going to go between 0 and 1. Okay, well, that's kind of nice because at least I got something to start with. Now, in math, they use y and x's and stuff. Well, this is electrical engineering. We don't use y. I want to know about voltage. So I'm going to rewrite this right here. I'm going to write it like this. I'm going to write this like V, and V is for voltage, equals sine theta. And so now my job is done. I needed an equation to describe an AC voltage, and there it is. If you tell me the angle where that coil is of the generator is in the magnetic field, I'll tell you what the voltage is at that position. Or if this is in time, if you tell me in time where that coil is as it rotates in the generator, again, I can, in time, and I'll show you that in a second, I can tell you what that voltage is. There's only one problem with my equation. This equation is perfect as long as the AC voltage I'm producing is no bigger than 1 and no smaller than -1. Because that's all we can get with this equation of the sine wave, which is what this is based on. The maximum value of the sine wave, or our sine function, is 1. The minimum is -1. So our generator, as long as it has an output max of 1 and a minute of -1, we're cool. The problem is you can't do anything anywhere with 1 volt of AC. That's silly. I need some kind of equation that no matter what my AC voltage is, that equation can represent it. So the mathematicians fixed that too. They said, all right, Mr. Engineer, here's what you can do. Instead of writing this like this, let me put a factor in front of that, A. We'll write this like this. And that A has a meaning that A stands for the amplitude. If you took trigonometry or your algebra class, when you talked about sine function and cosine functions, you talked about amplitude. So the amplitude, all that is the maximum height either this way or this way. So the amplitude here is 1 or -1, but when we report amplitude, we usually report the positive value. So that amplitude is just the highest value of voltage or whatever it is that you can get. And in this case, it's 1. And so how does it solve our problem? Well, pretty easy, because if I say let A, this is not writing, right? If I say let the amplitude equal 1, if this is equal to 1, then I got the equation that I had before for a sine wave. But if I need a bigger wave, then what I can do is, by having this factor in front, I can say I'm going to let A equal 10. So now I write this equation like this: 10 sine theta. So what happens if I do it that way? How does that solve our problem? Well, that's easy, because what it does is now I got 2 parts, I got 2 factors. I got the amplitude factor, which is 10, and I got the sine theta factor. Now remember, a factor in math, a factor, 2 things you multiply together to get a product. So this is my amplitude factor, and this sine theta is another factor. And so this is a constant. Nothing happens there, but the sine wave, this one, in this box, the biggest, it isn't a vary between 0 and the biggest it can be is 1, or it can go from 0 to -1. So all this thing in the box, this factor over here, sine theta, all that factor is going to do is vary between 1 and -1. So the biggest this factor right here can be is 1, and the smallest it can be is -1. But then what are we doing with the other factor? The 10. The 10 is taking this, and when it's 1, it's going to make y it's going to be 10 times that value. It's going to be 10. And when it's -1, it's going to be 10 times that value. It's going to be -10. So by putting that amplitude factor in front of the sine function, we can now stretch that sine function out to give us any value we want. Now we have a generator that can have a output voltage of 10 volts or -10 volts by just putting that amplitude factor in the front. Okay, well, that's kind of cool. So instead of writing it like this, I want this to represent a generator that can give me any voltage output from 0, amplitude of 0 to infinity. So I'm going to stick the amplitude factor in front of here like I did here. Only in math, they call it amplitude. They use that A. In electrical engineering, we don't use the word amplitude. We use either the value peak voltage or max voltage. So I'm going to write, instead of putting the amplitude here, AM, like you do in math, I'm going to use the engineering replacement for amplitude, which is the peak value or the maximum value. So our function to describe our generator is going to look like this. It's going to look like, instead of Y, engineers use a V. Instead of an A for amplitude, I'm going to use a V, P. That's a capital V. Now this is important. That's a capital V, and that's a P. And this is like a lowercase script v. The size, the way I present those symbols means something. I'll tell you that in just a second. So I got this VP sine theta. So now that's what I'm looking for. My grandmother would say, now we're cooking with grease. Because now I can take this equation. Now you tell me where's my pen? You tell me anywhere in that field where that generator coil is, you give me the degree it is away from the 0 axis, anywhere in that as it turns to 360 degrees, I can tell you what the voltage is going to be. Now look at what's happened. If the generator coil is right here at 0 degrees, I'm looking at the phasor of the generator coil with respect to the positive x-axis. At 0 degrees, if you got your calculator out, the sine of 0 is 0. That means the voltage is going to be 0. As it starts to go around up to 90 degrees, you take the sine of 90 degrees on your calculator, the sine of 90 degrees is 1. So when I got 1 here, my actual value is going to be the amplitude times the 1, which in this case was 10. So using the numbers I have on the board already because they're convenient, in this generator I get a voltage that actually alternates between positive 10 volts and negative 10 volts. But the actual value, now listen, the actual value of the voltage depends on when you look at it. The actual value of this voltage depends on when you look at it. If you look at it right here, the voltage is 0. Look at it right here, it's 10. Look at it right here, it's -10. Look at it right here, it's somewhere between 0 and 10. So the voltage, this voltage, depends on when you look at it. And so the name of this voltage is called the instantaneous voltage because it depends on the instant in time when you look at it, when you read it. So let me clean this up, and I want to write this out because it gets a little more complicated when I'm showing you. Here's what we got so far. We were looking for an equation to describe what's happening in that generator. And the mathematician gave us one. It fell right at us. They already knew about it. We just had to change the symbols around to reflect engineering. And so what we have is this. That for AC, you got a mathematical model or an equation that describes an AC voltage. And it looks like this. And what I said is that this value right here is called the peak value. It's just the amplitude or the height. And this value It's called the instantaneous. It's called the instantaneous value. Now, we're starting to get into notation here, so I'm trying to move slow. I can't see what you guys are doing, so I'm hoping you're writing this down. I'm trying to move through this slowly, and it gets complicated because now the sizes of different letters start meaning that. Just follow what I'm doing. If I have a capital letter like this one, that for now represents some kind of a peak value, some kind of an amplitude. If I have a lowercase script letter like this one, then that represents an instantaneous value. That means that it depends on when I look at it, it's the value I get. I'm saying that because I'm showing you all these equations in terms of voltage. I got an instantaneous voltage here. I got a peak voltage here. So I'm showing you all the equations tonight will be in terms of voltage. But whatever I say about voltage tonight is also true for current. All you got to do is replace the V's with I's for current. So I'm saying that I can write the same equation. I can say I got I peak sine theta, and it's exactly the same equation. Over here would be, and I want to show a little script I. And this will be the amplitude of the current, and this will be the instantaneous value of the current. Now, I'm not going to show I again tonight. You just got to remember, whatever I say about V, whatever equation I come up with tonight, that has either a script V or another V in it, you can take those V's out and put an I in for it. You just got to make sure where I have a script V, you put a script I. Where I have a capital V, you put a capital I, and those equations will be valid. Don't forget that. So we're good now, guys. Look, we have an equation that describes the voltage output of our generator, our rotating machine, and I'm good. We can pack up, go home, give me my paycheck. I'm happy. I did what you told me to. But I'm not happy with that. You see, we can drill down deeper here. I want to know more about this machine, so let's see what else we can get out of this. So I'm going to go back. Now remember right now, here's our mathematical model or equation that we're going to use to represent that generator. But I want to see what else we can squeeze out of this. So I'm going to go back to the picture of the phasor. Here's my model again. Script V is VP sine theta. And what I had before was I had the coordinate system, and I put my phasor on the coordinate system. Now remember what that phasor is telling us. All that thing, it's not hard. All the phasor is I took an arrow. I literally took an arrow and I attached it to the coil of my generator. When that generator spins around, the arrow's going to spin around. And instead of watching the arrow over here, I can draw it and I can actually think about it over here on this XY coordinate system. Kind of slick. I like it. So whatever that's doing is what this is doing. But by definition, we said that when we have a phasor, we're only going to allow our phasors to rotate counterclockwise. A phasor can rotate any way you want. But by convention, and what that means is a gentleman agreement amongst all engineers of any work that we're going to rotate our phasors counterclockwise. You can do that or you can not do it, but everybody else is going to do it. So phasors by convention, which means by agreement, rotate counterclockwise. All right, well, let me see. I want to massage this and see what else we can squeeze out of it. So let me see what else we can do. See what I can come up with. I have an idea. You guys know what a firefly is? Anybody know what a firefly is? I don't know if you call them fire. I call them lightning bugs. What do you guys call them? You call them fireflies or like, huh?
Lightning bugs.
Lightning bugs. Who was that? Jacob? Who
Cole.
was that? Cole? Cole, where you live? Are you from Cincinnati?
Melbourne, Kentucky.
You're Kentucky, okay. Because sometimes people come from like when people I have family in California, and I think I went to California and I wanted to pop. I wanted to drink. So I said, let me give a pop. They said, a what? A pop. What's a pop? They call it soda. When I had on gym shoes, they said, what are gym shoes? They call them sneakers. And so when I say lightning bug, sometimes I get students, what the heck is a lightning bug? You mean a firefly? Whatever you want to call it, I don't care. But here's what I want to do. Let's say I took a firefly or a lightning bug, and I put it right here. I always pick up a pen that doesn't write. That janitor's going to be really mad at me because I keep throwing these markers everywhere. So I got my firefly. Actually, I need another. Ooh, I got a bunch of markers here. All different colors. You need a lot of coloring pens and pencils. Now, I said 4, but look at all these I got. Somebody last semester bought me a whole bunch of markers. And I actually got almost every color in the rainbow. I got some more in another bag. Orange. So I got my firefly right here. Now you might say, well, why are we putting a bug on there? The bug lights up, and what I'm going to do is I'm going to let this generator coil just spin around, which means this phaser is going to spin around, and then I'm going to turn the light out. If I turn the light out, when that firefly is flashing off and on, what will I see? Now, guys, if you can't answer this question, you need to withdraw from the class.
I'm telling you. The instant value?
No, I have. You saying at Kings Island, these kids will get those things that light up. It has a light bulb under, and they spin it. What shape does it make?
A circle.
A circle, right? If I have a lightning bug here, he's blinking off and on. I let him spin around, and I turn the light off. You're gonna see a circle. That's all. Now you might say, okay, now you really lost me, Singleton. Why the heck are we looking at lightning bugs on phasers? And what difference does it make that it produces a circle? Well, because what I'm trying to do is I'm trying to come up with an equation that explains the situation. And I don't know, you know, all too often we get an equation. Everybody's had DC. Everybody knows Ohm's law or Watt's law, and we use the hell out of it. But to come up with that simple I equals V over R, it took a long, long time to come up with it. Now it's obvious. I laugh when I read books and say, oh, it's obvious that. It was not obvious to the person that found it, that discovered it. Trust me. And so we're trying to come up with a model that describes nature, this nature. And so I'm doing almost anything now to come up with enough. So I don't know, I was bored, had too much to drink. So I took a lightning bulb, I put on my phaser, turn the light out, and see it makes a circle. Okay, what can I do with that circle? Here's one thing you can do. Think about this. If you have physics, I'm going to mix these up. Now, my background is in physics, so I know there's a difference between speed and velocity, accelerate. There's a difference. Some of those are scalars, some are vectors. I'm going to use them. I don't really care if it's a scalar or vector. I'm going to use the word in the wrong way. If I know the distance something travels, and I know the time it takes to go that distance, and I can get the velocity. For example, if I travel a distance of 100 miles, and the time it takes me to go that 100 miles is 2 hours, then I can say I'm traveling 50 miles per hour. This velocity is called the tangential velocity. Tangential velocity. Now, the tangential, that word is derived from the word tangent. Tangent, like in math, a tangent. And tangent means if I have a curve, a tangent line is just a line that touches a curve in one place like that. And so I'm saying that even though this thing is traveling in a circle, if I do this, let's say I let the phaser travel from, where's my blue Oh, my hand. Let's say the phaser starts right here at this position. And I let it travel all the way up to here. But I got a stopwatch. So it starts right here, and I start my stopwatch. And when it gets right here, I stop it. So now I know the time here we'll call T1. The time here we'll call T2. So I know the time. If I take T2 minus T1, then I found the time it took to go from point A to point B. And then what I can do is get a piece of string and put that piece of string right here and measure this length right here. I want to measure this length, and I know the distance. And what I'm showing you here is that if I know the distance something traveled, and I know the time it takes to travel that distance, then what I get is the velocity of that firefly in this case. Now, what good that's going to do us, I don't know, but it's a number. We're trying to come up with a number to help us out here, and it's a number. I don't know what we're going to do with it. What I'm looking at, though, is this. If I look at this diagram, the representation of this phaser, which represents the coil rotating in the generator, if I look at that, I see that now listen, I see that this distance is changing with time. This distance is changing with time, and this is what I came up with. Can anybody else look at this diagram and tell me any other thing up there, any other quantity that's changing with time? I'll be quiet. What else in this picture is changing with time?
Instantaneous voltage.
You're thinking too deeply about it. I got a phaser here, right? That phaser is rotating. And I can see that this distance is changing with time, right? It starts here, as it goes around, the distance is getting bigger and the time is getting longer. So I'm asking, in this picture, as this thing rotates around, what else is changing in there?
The speed.
The what?
The speed.
I didn't hear you breaking up. I'm hoping you said what I wanted to hear. What else? He sounds like he's fighting his microphone. All right, I'm gonna mute him. That's Daniel. Okay, Daniel said the speed. Okay, you're shooting blanks now. You're gonna be mad at me when I tell you what I want. What'd you say?
The angle?
The angle. Who was that?
Garfield. Garfield.
Yes, it's the angle. Garfield, you got an A for the course. You don't even got to take the rest of it. You get an A on your report card. The angle's changing with. Look. As this thing goes around, this angle right here is getting bigger. This is the angle theta. It's getting bigger as it goes around. So the angle is changing with time. So look, if I take the distance and I divide it by the time, I get something called the linear velocity or tangential velocity. If I take the distance, the distance of this line here, I take the distance, how the distance changes with time, it gives me the linear velocity. But as was mentioned, the other thing that's changing is this angle. So if I take the angle and look how it changes with time, I don't get the linear velocity, I get something called the angular velocity. I should write that all the way out. The angular velocity. Wow. Now, you all heard of this already. All I'm doing is I'm looking at how an angle changing with time. Instead of how distance changes with time, linear velocity, how does the angle change with time? The change of the angle with time is the angular velocity. You ever heard of RPMs, revolutions per minute? Anytime you think about you're really just talking about this. So you've heard of it. So If I'm talking about the linear velocity is the distance divided by time, but the angular velocity, well, here's what they use for angular velocity. It looks like a W, like this. That's actually the Greek letter omega. And you might say, well, hold on, Single. Last semester, you said that this was an omega for ohms. Well, it is. That's a capital omega. That's a Greek letter. This is a lowercase omega, right? So what we do is we use a lowercase omega to represent velocity, not the linear velocity, but the angular velocity. The linear velocity is the distance divided by the time. The angular velocity is the angle divided by the time. So I can write it like this. I can say omega, the angular velocity, is the angular distance divided by time. Now, you were taught to measure an angle in degrees, and then there's radians. And usually when we meet face to face, I go in, I talk about, I'm not going to do that tonight. I'm just not going to do it. You can look up on YouTube what a radian is if you forgot. But you can measure degrees, or you can use radians to measure angles. In this class, here's what we do. When we're making an actual physical measurement, we use an instrument like an oscilloscope, or we actually measure in degrees, we calculate in radians. I'm going to say that a second time. We measure in degrees and calculate in radians. Okay, so anytime I have some measurement I'm going to make, I need to know how many degrees out of phase with these two sine waves. I'm going to actually measure it on the scale. If I want to do something with that number, some math with it, I'm going to change it to radians. I'm saying that because this distance right here could be in miles per hour, or the unit could be meters per second, but the angular distance can be degrees or radians, and this is always in radians. That's in radians, and t is always in seconds. So my linear velocity can be meters per second or miles per hour, but my angular velocity is only going to be radians per second. Now, if you want to, if you brush off some of your trig, you can convert radians per second to revolutions per minute, RPMs. And that probably make more sense to you, especially if you're a mechanical engineer. But in this class, we deal with radians per second. So I have I take the linear distance. Let me slow down. I'm getting excited. I love this stuff. If I take the linear distance divided by the time, I get the linear velocity. If I take the angular distance divided by the time, I get the angular velocity. This tells us how fast something's going in a straight line. Well, hold on a second. That couldn't be right, because this lightning bug isn't moving in a straight line. It's moving in a circle. It's true that if you stand back and look at it, it's moving in a circle, but at any instant in time, it's moving in a straight line. Let me say that a second time, because you don't believe me. What I said was, it's true. If you stand back and look at that firefly, he or she or it is moving in a circle, but at any instant in time, it's actually moving in a straight line, and that's the velocity I'm talking about here. For instance, when it's right here, the straight line is right here. Or when it moves up to here, then the straight line is right here. So at any instant in time, it's actually moving in a straight line. Think about it like this. If you take a stick, got a stick with a string on it and a rock, and I spin it around. If you're looking down at the top of it, what you'll see is just like the lightning bug. You see it spinning around. While that string is spinning around, while the rock is spinning around, if I spin it around, while it's spinning around, if I cut it, it doesn't keep going in a circle. It's only going in a circle because the spring is pulling this way. The string is pulling down this way, and you're moving it that way. That forces it to go in the circle. But if I cut the string, it's going to move off. If it's at this point, it's going to move off in a straight line. So at any point in time, that rock is really moving in a straight line, and so is the lightning bug. So that's this velocity. But that's not what I'm talking about. I can look at the change in distance, the linear distance with change in time. That gives me the linear velocity, that's usually in meters per second, or I can look at how fast this angle changes with time. That gives me the angular velocity. The linear velocity is usually in meters per second. The angular velocity is always in radians per second. Radians per second. You might say, okay, Singleton, I get all that, or I kind of get it. But how's that helping us out with this? Look at this. I got a theta right here, which is the theta right here, which is the theta right here. So if I do this, what happens if I take this equation and I multiply this side by t, and I multiply this side by t? What happens if I do that? Who can see it? What cancels out?
The time.
Time, look, time, that's gone. And when that time cancels out, what I get is theta equals omega t. Which theta? That theta. So now what I can do is this. Since theta equals omega t, I can rewrite this. That says the instantaneous velocity equals the peak voltage sine theta, where theta is equal to omega t. So now what we have is this. I got this, we call that the instantaneous instant voltage. That's voltage written as a lowercase script v, or if it was current, a lowercase script I. This right here is our peak voltage. I'll just say peak value, or the amplitude. This right here is the angular velocity. The angular velocity of what? It's the angular velocity of the phasor, but since the phasor represents where the coil is in the generator, it's actually the angular velocity of the generator. So now this is overly cool, because now you're saying that, well, let me show you what the equation might look like. I might give you something like this. I might say that script V equals 150 sine 377t. If I give you that value, what can you tell me about that AC waveform?
Peak value is 150.
The peak value is 150. And if you draw a picture of it like this, and that's time, you can tell me that the peak value, oh, this is so good. I'm actually helping you with your homework and you don't even know it. You can tell right away the peak value is just by looking at that, the peak value is 150 volts. You can also tell me that down here, the negative, that's a minus 150 volts. How fast is the generator coil turning? How fast? That's omega. It's turning at 377 radians per what? Second. So just by looking at that equation, you can tell me the peak value, the negative value, and you can tell me the velocity of the generator. And if you wanted to, if I paid you enough money and gave you enough time, you can do a little math and convert, because people don't think in radians per second, you think in RPMs, revolutions per minute. But it's an easy calculation to go from 377 radians per second to revolutions per minute. We can do that if you wanted to. You can do it. So now I'm digging this. We changed our equation a little bit, and we got way more information out of there. I'm digging this. I want to take a break, but I'm on a roll now. So let me get off my natural high that I'm on, get through this, and then we'll take a little break. I don't want to stop now because I'm on a roll. Okay, well, I'm happy, but still not completely happy. I want more. I want all of it. So what else can we do with this? Well, let's go back to our diagram, our lightning bug. Go back to our lightning bug. Oops. So I have my phaser rotating in here. I have my lightning bug on there. And you know, every time it goes around, if I turn the light out, it's gonna make a circle. So now let me go back to something I said earlier. Remember this word right here? We said the period was a time for one cycle of the AC waveform. But how do I get an AC waveform? I get an AC waveform every time this phasor starts at 0 and goes around 360. I showed you the shadow projection of that phasor on my screen. Every time it goes around the circle one time, it produces one sine wave. It produces one of those. Every time it goes around one time, it produces one of these. So the period, by definition, is the time for one of these cycles. We use a capital T. Capital T, and I put these sides on it. We use that to represent the period. The period is the time for one cycle, the time for one of these. The TIME, the time for one of those. That's the period. Well, if the period is the time for one cycle, and I get one cycle every time I go around the circle one complete time, then what that period is really telling me is the time it takes the phasor to start at 0 degrees and go to 360. The period tells me the time it takes that generator coil to go around one time. The period. All right, so we got period. We got frequency. Now, I want to be very, very clear, because so many people can use those words, but don't know what the hell they're talking about. The period is the time for one cycle. The period is the time for one cycle, but one cycle is created when the generator coil goes around 360 degrees one time. So really the period is how long does it take that generator coil to go from 0 to 360? That's the period. The frequency. Okay, let's go back to my phasor and say this is your eyeball. Here's your eyeball. You're looking at this thing. Where's my prop? Here's my phasor. So this phasor is spinning around, and however long it takes to go around one time, that's the period. But now what you're going to do is you're going to count the number of times it takes to go. You're going to count the number of times it takes to go around. The number of times you're going to count how frequently it goes around. Imagine sitting on the side of the highway, which I wouldn't recommend doing, but let's just say you're doing it, and these cars are going by. Woof, woof. These cars are on the expressway going by, and you want to know how frequently a car goes by. So you say, all right, in 1 second, I'm going to see how many cars go by in 1 second. Woof, woof. Maybe 3 cars go by in a second. Or 5 cars go by in 5 minutes. I don't know. You want to know how frequently a car goes by. Here I want to know how frequently the phasor goes by, which is telling me how frequently the coil is going around in 360 degrees. How frequently is the frequency of the waveform. If this thing goes around 3 times in 1 second, it has a frequency of 3 times a second. If it goes around 100 times in 1 second, well, that's really frequent. It's 100 times in a second. The frequency is how often this phasor or generator coil goes around in a second, by definition of second. Now let me show you a picture. We use 1 second. I call it a time space. A time space. And remember, every time that coil goes around one time, it makes one sine wave, right? If I'm going to fix the time, if I look at it, I'm going to fix the time. I'm going to say, all right, I'm going to look for 1 second, then I'm going to look away. Or maybe I'll look for 1 minute. That might be my time space. See how many go by in a minute, I'll look away. The time space can be whatever I want. I might look for a whole hour, then look away. In engineering, electrical engineering, our time space is 1 second. I'm going to look and see how many times it goes around in 1 second. I'm going to count them, and that's going to be my frequency. So here's my time space. That time space is 1 second wide. 1 second. If the coil goes around one time in that second, if it goes around one time, it's going to produce this. Because every time it goes around one time, it produces a sine wave. But let's say we speed it up. Let's say the phasor or coil goes around 2 times in a second. If it goes around 2 times in a second, then it's going to look like this. See it? If it goes 10 times in a second, then I got to draw 10 of them over here like this. I have a time space of a second, so if it goes around faster, I got to scrunch more sine waves in that time space of 1 second. So as the frequency goes higher, the number of cycles in that second, the more I see, the more scrunched together that they are. So I can see, actually let me show you here. I've got a picture here. You can easily see, look right here. I'm talking about right here. It's showing you, here's the period. You can see this waveform right here. And this waveform right here. You can see the one at the bottom has a higher frequency because there's more cycle in this time. Say that's the time of 1 second. That might be 1 cycle per second right here. This might be what? 1, 2, 3, 4, might be 4 or 5 cycles per second. So the more scrunched together those sine waves are, the higher the frequency. So, period is the time for 1 cycle. Frequency is how many cycles happen in a second. And we use a capital T for period. So we use this script T like this. And for frequency, we use a script F. And so in the old days, let's say the generator coil went around 10 times in a second. They would say the frequency is 10 cycles per second. So if you ever seen that unit, CPS, that means cycles per second. But somewhere along the line, I don't know when, they went from cycles per second to what we call hertz. So 1 hertz is equal to 1 cycle per second. So instead of writing 10 cycles per second, you probably would see 10 capital HZ, 10 hertz. And remember, if I have a unit that's capitalized, that means it's named after somebody. So that hertz, it was Heinrich Hertz, I think it was a German dude. He got a unit named after him. So, but here's the takeaway. The period is how long does it take the coil to go around one time? The frequency is how often does it go around in a time space of 1 second. If I give you 1 second to count, how many times does it go around the circle? And there's actually a relationship between these two. The period equals 1 over the frequency, and the frequency equals 1 over the period. So write that down. Write it down. I'm almost at a point to where we can get a break. So, but you're in your living room or bedroom anyway. You can take a break anytime you want. And none of you are man enough or woman enough to turn your camera on so I can see what you're doing. So you might not even be there. You might be in your bed. You might be with your girlfriend or boyfriend. You might not even be listening to me. You know I'm going to record this. I'm not going to listen to that stuff. I'm going to put my camera on. You're going to think I'm there. I'll watch the recording later. Problem is, if you do that, you can't answer questions. I mean, you can't ask questions and get answers to them. So hopefully you're watching this. So I'm almost at a point where I can take a break, and then we'll take a break. But I want to dig a little bit deeper, because look at this. Think about this. Remember we talked about the angular velocity? Remember that? Remember when we said omega equals the angular distance over time. Remember that? So now I'm going to be very impressed. I'm going to ask a question. I'm going to be very impressed if somebody gets this. This lowercase t here, that's like an x. You know, you have, you might have y equals 2x plus 3. Well, that would be my independent variable, and that's my dependent variable, right? Well, in this class, we're not using x's and y's. We're using b's as in Victor and t's as in Tom. So we might have something like this. We might have script b equals 150 sine 377t. Now, that t acts like the x did in the other equation. That's our independent variable. You tell me what time to look at it, and I'll tell you what the instantaneous voltage is at that time, right? But what if I told you this? What if I told you to let t equal the period? If I say let t equal the period, in other words, if I change this from a little t to the period, then what would I put in here for theta? I'll be quiet and let you think about that. Now think about it. I took out the script t. This is any old t. I'm saying, no, don't look at it at any old t. Look at it at a specific t. Look at it at whatever the period is for that generator. Look at it at that time right there, that t. What would I put in here for theta?
Uh, 2 pi.
Yes! Oh, you didn't see that. I got to regain my composure. Who is that? What's your name? Who is that? You're not going to tell me who you are?
Oh, it's Mandy.
Thank you, Mandy. You made me lose my composure, man. I'm supposed to be cool and laid back. You made me go crazy. I love this. She's thinking, look, here's what she said. Well, hold on a second. If the period is, the definition of period, what we said, the definition of the period is how long it takes to go around one time. So if that's how long it takes to go around one time, I know that the distance around any circle is what? 2 pi radians. So if I put a little t down here, I don't know what to put in there for theta, but once you tell me that the t I'm looking at is the period, then the distance has to be 2 pi. Because there's 2 pi radians around any circle. That's what she saw. And look at this. Look at that. T is 1 over f. So if I wanted to, here's what I can do. If I wanted to, I can write this like this. I can say omega equals 2 pi times 1 over the period. But 1 over the period is equal to the frequency. I can get rid of that and put in that. So omega is 2 pi f. Omega is 2 pi f. So now, remember my equation I had before? Here's what I had before. Actually, there it is. I had this. I had script v equals vp sine omega t. But then I said script v is equal to 150 sine 377t. I said, all right, given this equation, what can you tell me? What you said was this. You said, all right, Singleton, I know the peak voltage. I know the peak voltage is 150 volts. I can tell you that. What else can I? Singleton, I can tell you how fast the generator down at Duke Energy is turning. I can look right here and say omega, that's the angular velocity. That means the generator coil is turning at 377 radians per second. I know you don't like thinking in radians per second. You pay me a little bit more money, I'll convert it to RPMs for you. If you want to pay me, I'll do that. But now, look, now that I know omega is 2 pi f, what I can do is this. Since I know omega is 2 pi f, and omega is equal to 377, then what I'm saying is 377 is equal to 2 pi times the frequency. And if I know 377 is equal to 2 pi times the frequency, then if I wanted to, I can solve this for frequency. Frequency is going to be omega over 2 pi. Now, I need you get your calculator out. I need your calculator. The frequency is going to be omega over 2 pi, but omega is 377 radians per second divided by 2 pi radians. So I need for somebody to take 377 and divide it by 2, and then take that and divide it by pi. Tell me what you get.
60 hertz.
60 hertz. 60 hertz. So the frequency is 60 hertz. Does that ring a bell for anybody? 60 hertz?
That's the frequency that all our power is generated at.
Yep. In the United States, the frequency of the power coming out of the wall outlet is 60 hertz. In Europe, it's 50 hertz. If you're on TWA on the plane, it's 400 hertz. If you want to know why it's 400, ask me later. But look, we went from just a simple old equation, y equals sine theta, and now without doing, I don't even need to see your generator. I don't care what your generator looks like. I'm telling you the amplitude of your generator. I'm telling you how fast your generator coil is rotating. I'm even telling you the frequency of the voltage that your generator's putting out. I think you need to pay me more money. I want a bigger raise. I'm not done yet, though. If I know the frequency is 60 hertz, what else can I get? What else can I tell you? What's 1 over 60?
So in the period is 0.0167.
It takes your generator coil on about 17 milliseconds to go around one time. Wow. I had a lapel up full on. I just feel like I'm just all powerful now. You see it? So I can really write this like this. Our equation for AC now is like this. Script V equals Vp sine omega, but omega is 2 pi f t. That's what it looks like. And so now, no matter what I give you, if I say, all right, here's your waveform, it's going to be 75 sine 490 t. You can give me all kind of information now. Wow. Okay, well, I promised you a break. So here's the time. Let's take a break for about maybe 5-6 minutes. And I want to come back. And here's what I want to do. We're almost done. I want to, I know you think this is complicated enough. There's actually one more piece we got to add to this. I want to do that. And then after we do that, I want to show you all the different ways we can write an AC waveform, and then we'll do some practice problems, and then we'll call it a night. So we should be done here, within the hour, I would say, okay? So let's take a break, maybe come back at, let's say 10 minutes if you want. Now, I hate that because that means on the video, you got this long pause, but it is what it is. Take a break. I need a break anyway. Fill up my bottle. And I'll come back in about 8 minutes. Let's just say 8 minutes, and then we'll finish up what we talked about tonight. All right, we'll start back up in about 30 seconds. So hopefully you guys are back from your breaks. 30 seconds. All right, so on the board, I have a list of ways you can express an AC waveform. And what I'm going to do is I'll describe each one of these. But remember what I said earlier, I'm going to describe everything in terms of voltage. Whatever I say about voltage is also true for current. So in the equation, you'll have a script V or a uppercase V. Just substitute the script V for script I, or the uppercase V for uppercase I, and you have the equivalent equation for current. Now, I'm going to give you a quiz over the weekend. I'm going to give you a lab to do over the weekend. Then I'm going to give you a quiz to do over the weekend. I think quiz one, I gave quiz one. I think that was about what grade are you going to get or something like that. Well, quiz two will have more to do with what we're talking about tonight. But the stuff I'm about to go through right now, and then the example problems we'll do tonight, when you finally come in, like let's say we come in next week, this will be a quiz you'll do where you'll need your calculator. It'll be the first like in-class calculator quiz that you do. So you want to make sure you take good notes on this part and that you understand what I'm talking about and you're able to make these calculations. They are very straightforward, so I don't perceive that you'll have any trouble with anything. But if you do, please let me know, and then I'll go over it until you understand it. So we have 6 ways that I can express an AC waveform. We already talked about a couple of these, but I'm going to go back starting with number 1, explain what it is, and show how we represent it. So the instantaneous value, the word instant is in there, and instance has to do the time you look at something, right? So the instantaneous value is always given from a graph. I mean, I can tell you what it is, but basically you have some kind of graph. And on this axis, you can have voltage or current. You got a waveform. And if it's an instantaneous value, this axis will always be time. And then, depending on what the person says, hey, look at it at this time. If I say look at it at this time, you can go up here. You can give me that value right there. That would be that's the instantaneous value for that time. If I say look at it at this time, you draw the graph up, and that right there is the instantaneous value at that particular time. So the instantaneous value is the value at a certain time. Typically, we don't really care about the instantaneous value. It doesn't really matter on a big level, like when you plug something into the wall, we don't really care about the instantaneous value. But since we're in engineering courses, engineering technology courses, you want to know what that is. So instantaneous value, the value at a particular time. I can have an instantaneous voltage, or I can have an instantaneous current, or later on, instantaneous power. We'll talk about that later. The way we represent an instantaneous value is with the script letter. So if it's a voltage, it will be a script letter V, lowercase v. If it's a current, it will be an I, a script I like that. The peak value. Now the peak value, we already went over that, but that's just the amplitude. So you know on a sine wave, there's 2 peaks. There's a positive peak. This is the peak here. So that would be my positive peak. And then down here, that would be my negative peak. So this height right there, either that height or that height. Now, this is not symmetrical, but these are the same. So that is that's called my amplitude. So electrical engineers call that the peak value. Sometimes you'll see VM, and that's for the max or maximum value. This depends on whose book you pick up. So in here, I talked about the peak value. We'll use a capital V with a little p as a subscript. So this is the peak value. I'm going to have a VP. I'm going to have a peak current. So this is an uppercase V, uppercase I, lowercase script V, lowercase script I. So just the symbols, the way you draw them, have meaning. So you got to draw them the right way. Okay? Now, this value, peak to peak value. The peak to peak value is the value from here to there. From this point to that point. It's the absolute value. So, what I mean by absolute value, I don't care that that's negative. Like if this was 100 and that's minus 100, if I add them together, I get 0. But that's not what I mean. The distance from here to here, the absolute distance, this is 100 and that's 100. The absolute distance would be 200. Okay, so the peak value is just this. It's just 2 times VP. So on my waveform, if I have an amplitude of 100, then my peak to peak voltage would be 200. You might wonder, oh well, why do we have? I have to keep muting Daniel's microphone for some reason. But why do we have that? Well, when you come in here for lab, the instrument you're going to use to measure AC voltage, the instrument you're going to use is called an oscilloscope. And on the oscilloscope, there's this grid, and you can make measurements on this grid. And you can make the measurement in peak value or peak to peak value, either one, it doesn't really matter. So we usually use either peak or peak to peak for measured numbers. But if I know the peak value, then the peak to peak value is just 2 VP. Now the average value is a little harder to describe. I want you to think of what an average is. Let's say that I give you a test and I walk in after I grade the test and I say, all right, the average value on this test is 73. What does that mean? Well, it has a lot of meaning because if you took statistics, you know it's several different kind of averages. But what we mean in that case is the way I would get that average is I would take all the grades, all the scores, I add them up, then I would divide by the number of students that took the test. And that would give me the average value. Most people fall around that average value. Well, that's kind of what I mean here, but we got a problem. If I apply the same logic to this, let me redraw this. You'll see what I'm saying. Let's say I want to find the average value of the sine wave. So here's my sine wave. And I got one cycle of the sine wave. And I want to find the average value of that sine wave. Does anybody see any problem with doing that? I got to add up all the values here. So I take the values here. For each of these values, I got to add them all up. So what I got to do is I got to take like the value right here, get that value, this value. I got to do this for the whole thing. Add all those values up and then divide by the number of values I have, just like I would for average on the test. Anybody see any problem with doing that?
Well, there's an infinite amount of values.
That's true, but we can still get an average. He said there's an infinite amount of value. I like that. That's a calculus thing. But we can still get an average. Something more evident than that. All these values right here from 0 to 180, all these values are what? I mean, look at this value. I got this value, that value. All these values are what?
Positive.
Positive. And then when I come over here, all these values are what?
Negative.
I got the same value on both sides, except for the values from here to here are all positive. I got exactly the same numbers over here, but they're all negative. So when I add them up, the average of a whole cycle of a sine wave is 0. The average of a sine wave is 0. So this doesn't really help us out with much. Well, it kind of does, because anytime in anybody's book you see the average value, they don't mean the average value of the whole sine wave. It's always the half cycle average. The half cycle average. So this value right here refers to the value of half the cycle. So here's how you would write it. You say V A V E, or you can say V A V G, either one. So that's the average value. Now, somebody answered and said there's an infinite number of values. And I was like, yeah, that's not really a problem if you know calculus. Because what you can do is something called integration. Even though you have an infinite number of values, thanks to Newton, we figured out a way we can handle that, right? We can use calculus, we can do integration, and we end up being able to calculate the average value under this curve right here, but we don't know calculus. So what the calculus people did, they did all the work for us, and they said that as long as you take the peak value and multiply that by 0.637, that'll give you the average value of any sine wave. You might say to yourself, okay, that's like magic, Singleton. Where did that 0.637 come from? Well, if you want to know that, you got to take calculus. But they should have you guys taking calculus anyway. I think that they should have you take algebra, geometry, trig, and then you should have to take calculus. I don't know if they still do, but our software engineering students, they all start off in calculus. If you don't take calculus, you're not getting that degree. It just helps you to understand so much. Like, then you would know where this number comes from. Anyway, that's not why you're here. All you want to know is, how do I get an A on my quiz? Well, on this question, you take the peak value, you multiply by 0.637 times the peak value, and that gives you the average value. Okay, now, the average value, you might say to yourself, well, hold on a second. Now, I'm not going to let you get away with that, Singleton. First of all, you threw half the waveform away. We're not even looking at these points over here. And then on top of that, what good is this going to do us? Well, honestly, it won't do any good in this class. But if you're electromechanical, you won't take this. If you're biomed or you're just straight EET, you'll take a class. What do we call it here? Electronics. Some places it's called semiconductor electronics, or solid state. But here we call it electronics. And then electronics, then that's where this value comes up. Because one of the very first things you'll do is, remember the process I mentioned when we talked about moving power around? So we generate AC power, we step the voltage up, we send the power out, high voltage, low current. Get the power where we need it, we step the voltage down, low voltage, high current, but now we got AC. But my TV, my computer, really wants DC. So you plug your computer in the wall, AC comes up into your computer, but there's a circuit in your computer called a rectifier. A rectifier. A rectifier takes AC current or voltage and changes it to DC current or voltage. So let me show you what that looks like. This is a topic for a higher class, but I just want you to see. What this rectifier does is it changes this AC to look like this. I got this waveform, but then it takes this and flips it up, makes it like that. And believe it or not, that's DC. Well, why is it DC? Well, because I'm used to DC looking like this. Well, this is DC. It's called pulsating DC. It's DC because the current never changes direction. As long as this doesn't dip below to the negative value, that means the current's only flowing in one direction. So what's happening here is the current starts off at 0, goes up to the peak value, and goes back to 0. And that's a form of DC, pulsating DC. Pulse. I think that's how you spell pulse. Pulsating DC. Now, that looks like this. Remember I said you take the average value of half of the cycle? So if you took the peak value right here, if you took the peak value right here, whatever that is, and you put that value into this equation, you get a value down here. You get a value, and that would be your average value. And then if you took your digital multimeter and put it on DC, and you put it across this waveform, then that value right there is what your DC meter would read. It will be your average value. Just so you know, though, if you take this class I'm talking about, and if you're biomedical and or your EET, you will take electronics. Once you get the AC using the rectifier, once you get it looking like this, what they do is they call them filters, and they put a filter on the rectifier, and it changes this pulsating DC to just regular DC. It's pretty easy to do. All the filter is just a capacitor. Point is, I can go from this to this to this, but in doing that, that's where this average value comes up. So you learn about average value in this class, AC, but you won't use it until you take electronics. So for me, you still got to be able to calculate the average value. All right. So, erase this. This is, all right, now, this next one is the most important one on the board. This one. That's the most important one. And by default, this one too. I'll explain that in a second. So this is called the root mean square value. And we usually abbreviate that RMS. Nobody ever writes it out like this. I wrote it out because I want you to see it, root mean square. The way the name comes about is if you look at the way the value, the calculus, if you look at the way the value is calculated, there's like a square root. So there's a root in there. There's a mean. A mean is like a special kind of average from statistics. And then there's a square in there. So something's raised to the second power. So they look at the operations you do to get this value, and they named it after that, the root mean square. But it's always short. We always talk about the RMS value. To get the RMS value, what you got to do, and again, the RMS value, there's a constant in here that comes from calculus. I'm just going to give it to you, and I'm not going to worry about trying to explain where the number comes from. But the root mean square value, right, as a capital V RMS, and it's equal to 0.707 times the peak value. Now, the reason I said that that's the most important one is most of the time you see a RMS voltage. Let me rephrase that. Most of the time you're given a RMS voltage, it's in this form right here, RMS. So, for example, when you if you buy a microwave or you buy a toaster or something, there's always a label on it. It'll tell you the power of it, and it'll say 120 volts. When they say 120 volts, do they mean 120 volts instantaneous? Is it 120 volts peak? I know you're thinking, is he about to go through this whole list? Yes, I am. Do they mean 120 volts peak to peak? Do they mean 120 volts average? What? Most of the time, really all the time, when you see a voltage, if it's not specified to be one of these, it's always RMS. The way we communicate voltage values or current values is RMS. So this is very important. So important that I'm not going to do it tonight because you're tired, I'm hungry, I got to go feed my dogs, I got stuff to do. So I don't want to be here till midnight. So what I'll do is I want to go into the details of what exactly does that mean, RMS? Why is it so important? Well, it'll take me a good hour to do that, at least 45 minutes, maybe a half hour. But I'll do that next week. You'll know exactly what I mean by this. So now, tonight, be able to calculate it, but I want you to know what it means. We'll talk about that next week. Okay, so let's put a star back by that. That is really important. Very, very, on a scale of 1 to 10, it's a 20. Okay? And this last one, I circled that too. The reason I circled it is the effective value is just another name for RMS. So if I write it out, the effective value, VEFF, is equal to VRMS, which is equal to 0.707 times the peak value. And again, that constant 0.707 comes from calculus. So you look at anybody's book, they're going to have a square root of 2. As you calculate these values, they always use the square root of 2. I don't do that. I don't use that square root. You'll see square root of 2 sometimes multiplied. You'll see square root of 2 sometimes divided. And I like the square root of 2. It's kind of nice to use because there's no decimals there. It's just a nice clean number. But I like to write everything in terms of the peak value because what you can measure off the oscilloscope right away is the peak value. So you'll see I have everything written in terms of the peak value. Peak to peak value is in terms of the peak value. Average is in terms of the peak value. RMS, all of it has a VP in there. So once you got VP, you're good to go. Okay? So that's the first thing I wanted to do here. So I wanted to go over these values. And now you got to be able to actually use this stuff. So let me pause for a second because I talked about a whole lot of stuff today. I was addicted to Diet Coke, and I got off. I beat my addiction. I was just, this stuff, I don't know what it is. I don't like regular Coke. I just like Diet Coke. And so I got off I kicked the habit. And for some reason, I'm back on it. So when you guys were on your break, I snuck downstairs and got a Diet Coke. They're so good, but it's not good for you. They put something in this. No, that's not what you're here for. Anyway, let's do some practice problems. So get your calculator, get your pen, get your pencil, get everything you need, and you have a sheet. I'm actually going to project it on the screen. What I want to do is I want you to go over. If you can do what's on this sheet, then not the quiz I'm going to give you this weekend. That's going to be something you do at home. But when you come in here, I'm going to give you a quiz. You got to calculate these values. And I'm telling you, if you can do what's on this sheet with no problem, you'll ace the quiz. So I want you to get a piece of paper, get your calculator, get your pens, pencils. And what I want you to do, get your topic sheet out. If you don't have it, I got it right here. I want you to do these practice problems on the bottom of this topic sheet. Now you got a little magnifier up here, you can blow these up. So at the very bottom of the paper, there's 10 problems. They give you a waveform. V script V is 167.5 times 455T. They want you to find the values listed below. They want to know the peak value, the peak to peak value, RMS value, average value, instantaneous value at 3 milliseconds, the frequency, the period, something about this thing called the wavelength, angular velocity, and then number 10, and once you come up with an equation. So get your paper out, your pen, your calculator. Go ahead and calculate this. I'll pause for a minute and give you a chance to go through it, and then we'll go over it to make sure you got the right answer. Once we do that, I got one more thing I want to go over briefly, and then we'll be done for the night. All right, so I'm going to give you a few minutes to work on this, and then I will be back on camera in a second, and we'll go over it. Okay, guys, I'm gonna give you about another minute, and then I want to go over these questions. About 1 more minute. Okay, hopefully that was enough time for you to start thinking about how to solve this. And what I like to do is just kind of write the general form. Actually, I got that backwards on. I want to write the general form. So I want to put right here. This is my VP sine omega t. So this is the general form. And then this was, what was it? Let's see if I have it. That was 167.5. All right, so I write the general equation up under it just so I can just kind of match the different values up. So we're given this expression, and they want us to find all these values. Peak, peak to peak, RMS, average. They want to find the instantaneous value at 3 milliseconds. They want you to find the frequency period, the wavelength, what's that? This thing called the wavelength, angular velocity, and then they want you to find the expression for the current. So let's start with the easy one. What's the peak value? How would I get the peak value? Make sure you guys are still in here. Yep. So how do I get the peak value?
From
The
the
peak value
equation.
is
Yeah, you don't have to calculate anything, you just look at it. So if anybody misses that, you're gonna be in trouble. Peak value is right here. So then I can just go ahead and just calculate. The peak is 167.5 volts. Now, sometimes what you do for this V here, you would actually write that as VP, or over here you can put a PK right there, so that people know that that number is a peak value. So however you want to do it. VP is 167.5. And then remember, everything else is in terms of VP. So these other values here, as long as you know what the constant is that you multiply by, then it should be a piece of cake. So VPP is just 2 VP. So anybody take, what's 167.5 times 2 is what?
335.
All right, so we got that one. So we good here, here, RMS, that's the important one. So VRMS, 0.707 times the peak value. So how much is that? .707.
118.4.
Okay, so this is important right here. Now, next week, I'll tell you what this number actually means. It's a specific meaning. And remember on the quiz, I could add, that's also called V effective. And next week when I explain RMS, you'll know why they call it the effective value. Okay, so that was easy to do. And then we go to the average value, V average. My constant 0.637 times the peak value. How much is that?
106.7.
Okay, so 106.7, well, what does that mean? 106.7. Well, remember, it doesn't mean anything in AC, but if you convert AC to pulsating DC using a rectifier. So you have this circuit called a rectifier that you'll learn about in electronics. A rectifier. It has an input and an output. And what the rectifier does is you put in this, you put in AC like this, what you get out is this. And whatever this peak value is right here, whatever that peak value is what the peak value is here and here. So if I take that peak value or this peak value, if I take that peak value and I multiply it by 0.637, it gives you V average. And V average, what that is this is AC, this is DC. So over here, if you want to measure that, you have to take your meter and switch it to AC. But when you want to measure on the output, that's DC, so you got to take your meter and change it to DC. What would your DC meter read? It would not read the peak value, it would read this average value. So if this peak value right here, that peak value was this, it was 167.5 volts. And when you put your meter to DC and you put it across that waveform, what you're going to read is about 107 volts, 106.7. So again, this is a topic later on. If you take electronics, which when you guys come in the lab, I have to talk to some of you because some of you can easily get a double major. You might be electromechanical, and by taking just a couple extra courses, you can get both your electromechanical degree and your EET degree, your full-blown EET degree, but just taking 3 or 4 more courses, so that's something we can talk about. At Cincinnati State, they award you 2 degrees. They don't do that at all universities. I went to Xavier and I took all the courses for physics and a degree in philosophy, but I had to choose which degree I wanted. They wouldn't give me both of them. They would say, all right, I'm gonna give you a degree in physics, even though you completed everything for philosophy too, but you get 1 degree. And on my record, it says this person completed all the requirements for philosophy, but they didn't give me a degree in philosophy, just physics. But here, you can take the degree in, let's say, your electromechanical and a second major. You get 2 diplomas, which is kind of nice, makes you really marketable. So, I'm saying that to say, let's say you're electromechanical. I don't think you take electronics, but you have in your curriculum where you can take what they call I forget the name of it, an optional course or whatever. I don't know what word I'm searching for, but you may be able to take electronics to count as something towards your major, and you can kill 2 stones with 1 bird. I said that the wrong way. Anyway, we'll talk about it. So we got all the way, got this done, this done. Now this one, I have this written in algebra. If you have, you've probably seen this in math, where if you have y equals 2x plus 1, I can write that in function notation. Remember function notation from algebra? I can call this f of x. So I can say y equals f of x. I can write this as f of x equals 2x plus 1. And then what that allows me to do is, if I want to put in the value for x, say I want x to equal 3. Well, I can say f of 3 equals, and then I put in 2. Wherever I have an x, I put in the 3. Right? That's what I'm showing here. This is a function here. This is really v of t. If I use function notation. And I'm saying, all right, what is v if t is 3 milliseconds? That's the notation I'm using here. You can use it if you want, I don't care, but if you're trained in mathematics, that's the way you write it. Now, you got to be careful here. You got to be really careful. Let me show you why you got to be careful. And I don't want you to forget this. On exam 1, if you make this mistake, you're going to lose a lot of credit. You're going to lose a lot of points. So watch what I'm going to do right now. Go back to this equation. Let me get some room here. If you think about it, let's go right here. So we have this equation that represents our sine wave. V is VP sine omega t. And I want you to focus on this right here, this part. The omega t part. That omega t part, omega t, omega equals, we said omega t was the angular, how do I want to do it? Well, let's just do it with the units, that would be better. So this is omega. So omega has the units, we got omega t. Omega has the units of radians per second. That's the units for omega. And t has the units of what? Well, t has the units of seconds. So by taking omega and multiplying it by t, what you're taking is a unit of radians per second, and you're multiplying it by seconds. And what happens when you do that is this cancels out, and you get radians. Now, why am I showing you this? Well, I'm showing you that that product of omega and t, the unit, the proper unit for that is radians. What does that mean for you? Well, that means that when you calculate this on the exam or quiz, when you calculate that, when you take the sine of this thing right here, you better change your calculator to what? Not degrees, but what? Radians. If you calculate this in degrees, your answer is going to be wrong. Because I'm showing you right here, the math is saying, hey, this product is in radians. So to give me the correct answer here, you need to, usually by default, your calculator is in degrees. You got to know how to change your calculator from degrees to radians. So to calculate this, you need to change your calculator to radians, do the calculation. Once you get the answer, change it back to degrees. The reason I want you to do that is sometimes on the exam, students either forget to change it to radians and they'll miss it because they'll have it in degrees, they'll give me the wrong answer. Or they'll remember to change it to radians, they'll do this calculation and get it right, but then they forget to change it back to degrees, and later on in the exam, you might need to do something in degrees. So on the quiz or exam, when given this question like this, change your calculator to radians, do the math, get the answer, then change it back to degrees is what I would do. But here's how you would do the problem. We have V of 3 milliseconds. So here's how you write it out. We have script V equals, and then this, 167.5 sine, in parentheses, put the parentheses, 455 t, but this is t right there. This is the t. So t is 3 milliseconds. Now don't put 3 milliseconds there. Write that out. 3 milliseconds is the same as 0.003 seconds. You want that in base units of seconds. So this is times 0.003. I'll leave off the units. Close paren. And that's how you get the answer. So sometimes students will close parentheses here. You got to close it after you take the product of the angular velocity and the time. Anyway, when you do the math, what do you get? Somebody tell me the answer.
163.97.
163.
Yep.
7. Okay. All right. Okay, so we're cooking. We're doing all right so far. So if you didn't get that right, make sure you understand what you did wrong. I think this is the right answer. I remember calculating that. But, make sure you do it right. The common mistake is either you don't close your parenthesis or you don't change your calculator to radians. That's the common mistake. All right, we'll keep going. We're almost done. We want to get the frequency. The frequency is always determined from this omega. We say omega equals 2 pi times the frequency. So I just solved that for F. F is going to equal omega over 2 pi. Now let me show you how these units work. My omega is this. This is omega. So I have, if I want to carry out the units, I have 455 radians per second divided by, now this is 2 pi, it's 2 pi, but the circle is 2 pi radians. So I just put that unit in there. A radian is kind of nice because it's one of those units you can put it in there when you need to cancel, take it out when you don't need it. So I can just stick in here radians. So my units actually work out because what happens is the radian here and radian here cancel out, and then what you'll end up with is, now I need for somebody in your calculator to get this right, put this in parentheses. You either have to take 455 divided by paren 2 pi close paren, or if you don't want to use parentheses, 455 divided by 2, and then divide that by pi. But either way, when you do this, what do you get for a frequency? F is what?
I think 72.4.
72.4. Now look at my units. I canceled this with that. So my units are 1 over seconds. Well, that's what a hertz is. A hertz, 1 hertz, is equal to S to the minus 1. It's equal to 1 over S. So a hertz is an inverse second, which is equal to cycles per second. Okay, so the units actually work out once you know that hertz is a second to the minus 1. And that's the right number, 72 hertz. 72 hertz. And of course, if you know that, you can get the period. I'm just taking 1 over the 72.4. Can somebody tell me what the period is? 1 over 72.4 is what?
13.8 millisecond.
All right. Now, this is weird. That upside down Y. What's upside down? Upside down Y. Well, that's not an upside down Y. That's the Greek letter lambda. Lambda. If you're wondering why I know all these Greek letters, is I don't know what came over me. I went to Xavier, UC, and Wright State. So I went to Xavier for physics and philosophy. I went to UC for my electronics and my general studies, and I went to Wright State for clean energy stuff. And when I was at UC, I don't know why, some said, you know what, I want to take some Greek classes. So I took a 5 credit hour Greek class. I was in there with all these super smart people. Well, yeah, they were pretty smart. And I was in this Greek class, and I got out of there quick. I mean, the only thing I learned was the Greek alphabet. I didn't learn anything else. I dropped that class and got out of there because it was way above my head. I was just a dumb physicist, a dumb physics student. I couldn't do all that stuff. Anyway, so this is a lambda, Greek letter lambda. And in physics, we use this for something called the wavelength. The wavelength. What's the wavelength? Well, this actually is interesting, so give me a few minutes to talk about the wavelength. So what the wavelength is, if you have a sine wave, so here's my sine wave. The wavelength is the distance from any 2 consecutive points. So I can go from this point to this point, or this point to this point. I like to go from this point to that point. So that lambda would be the distance between these 2 points. That's the wave length. You might say to yourself, well, hold on, you said that was the period. Well, it is the period. If you have time here and voltage or current there, then that's the period. But if I put Lambda here, that could be in like meters or inches or feet, then that's the wavelength. So the wavelength isn't the length of the whole curve, it's just the length from here to there. That's the wavelength. And you might be, or you should be, wondering yourself, well, okay, well, what good is that? Well, this is why this is my favorite class to teach. I love AC more than any other class in engineering because it brings in everything. It brings in physics, chemistry, math. It just brings everything together. It turns out that almost everything we're going to learn this semester, how do I say it? We don't teach this course here anymore, but they still teach it at UC, and I took it when I took my engineering courses at UC. It's called communication electronics. So think about this. Communication electronics is all it is AC without the wires. AC without the wires. And here, if I have a current or voltage, I got to hook it up to a wire. But here's what you don't know. When you have an AC current running through a wire, energy flows back and forth. It alternates back and forth through the wire, but it also radiates off into free space as a radio wave. And all these equations that we're talking about, like this one especially, works whether the energy is going through a wire or going through free space as a radio wave. And so what I'm saying to you is like your cell phone. Your cell phone, you can dial somebody up and you can ring the person on your cell phone. Well, the way you're connecting to them is through a radio wave. There's a small antenna in your cell phone. It actually generates a radio wave that connects to the cell tower. And the radio wave looks like a sine wave. Well, it turns out that the antenna in your cell phone, if I want to get a really good reception, not just your cell phone, but anything that works on the radio wave, like radio, TV, anything that's wireless has an antenna in it or on it. Well, that antenna needs to be the size of the wavelength or some multiple of the wavelength to work correctly. That's why it's important to know. So if I'm talking in this class where all of our current is on a wire, this really doesn't mean anything. But if you took the class communication electronics, which you can take anyway as a Cincinnati State student, you can register for that class at UC if you want to and pay our prices, by the way. But anyway, if you ever take a course like that, you want to know, all right, how big do I make the antenna to pick up this radio wave? Then I would have to calculate lambda. So it tells me how big the antenna needs to be. Okay, so we're going to find out something really interesting. Let's figure out the wavelength of this signal right here. Well, the way you calculate wavelength is they give you a hint. They said, what was my hint? I forgot. My hint is lambda, C equals lambda F. C equals lambda times F. Now, if you don't know C from physics, you know that this is the frequency. You know that's the wavelength, because I just told you. But this C here is actually a constant from physics. That's the speed of light. And you're wondering to yourself, well, why are we using the speed of light in the engineering class? Well, the reason you do that is when you talk about radio waves, a radio wave and a light wave and all those waves, they're all a part of what we call the electromagnetic radiation spectrum. It's all the same. A radio wave and a light wave all travel at the same velocity or speed. Travels at the speed c. I think I'll give you the number there on the paper. So it doesn't matter if you're using a light wave, talking about light, radio wave, any of those, all travels at the speed of light. So that's where that comes from. But what they ask us to find is, all right, let's figure out the wavelength. And the wavelength will tell us how big our antenna needs to be if we want to, say you got this wire and you put this signal on the wire. Most energy is going to go back and forth on the wire, but some of it is going to radiate off as a radio wave. And if it does that, if I want to pick that radio wave up with my receiver, how big should my antenna be? That's what the wavelength can tell you. So let's figure out the wavelength for this waveform, if this is my waveform. Let's figure it out. Well, it's pretty easy. All I got to do is solve this for lambda. So if I solve that for lambda, see, lambda, the wavelength, would equal, I got to take the speed of light and divide that by the frequency. So if I solve this for lambda, that's what I get. And then on the paper, he tells you the speed of light is 3 times 10 to the 8 meters per second. That's 186,000 miles per hour, miles per second. So C equals 3 times 10 to the 8 meters per second divided by my frequency. Well, if you remember my frequency, you told me the frequency was 72.4 hertz? So down here, I'm going to put in 72.4. But since this is seconds, and I know a hertz is an inverse second, I'm not going to put in hertz, put in 1 over seconds, because that's what a hertz is equal to. So all you got to do to get the answer here is take 3 times 10 to the 8th and divide it by 72.4. Tell me what that number is, and that's our answer. Let me know when you got it.
4.14 times 10 to the 6 meters.
4.14. Is that right?
Yes.
Times 10 to the 6 meters. So let's do that another way. Let's write that as a decimal number. Anybody else get that number? Just to double check.
Yes.
Okay. So let's write that as a decimal number. So that would be 4.14. I'm going to take it out of this, right? And so that means I got to move it over 6 places. 2 of the places. It's already here, so I got to add 1, 2, 3, 4 zeros. So this will be 1, 2, 3, comma, 1, 2, 3, comma, and that would be meters. Did I do that right? So here's what that's saying. Here's what this means. If I have a frequency of 72 hertz, and I want to pick up the radio wave radiated off the wire that signal is traveling on, my antenna would have to be, that's how big my antenna would have to be, or some multiple of this. I don't really have a good feeling for that. So do me a favor. If obviously on your computer, go to Google and put this number in. Ask Google to convert this to miles. You can type in 414,000 meters to miles. If you do that in Google, it'll automatically convert it to miles. How many miles is this equal to?
(2,572 miles).
Okay, now this makes a little more sense. Now, you probably don't know this because you guys are born in the era of, GPS. I'm old school. When I travel, I use a map. So I know from Cincinnati to California, it's approximately 4,000 miles, about. And I know that this is a little bit more than half. My antenna would have to reach almost halfway to California. That's a huge antenna. If my frequency, look at this equation. Look at this. Lambda is C over F. Lambda is C over F. So I will write that like this. Lambda is directly proportional to 1 over F. You can see from the equation that if I have a low frequency, then my wavelength is really big, like this one, and I will need a really big antenna. If I want a small antenna, what I got to do is take my frequency and make it really high. That means my wavelength is low, and my antenna can be really, really small. So on your cell phone, on your wireless computer, on all of those devices, when they have the frequency of the radio wave, it's always in megahertz or gigahertz. Mega's 10 to the 6th. Giga is like 10 to the 9th, I think. It's 10 to the 9th. But it's a high frequency. So if you're wondering, well, why are the frequency of these devices so high? Is that so they can make the antenna really, really small to fit inside your cell phone? Now we're getting to all this stuff, which is just kind of a side note. just by looking at the math from this. This is pretty cool stuff. Just from the math, we can reason about antennas. We can go 1,000 different directions and understand a whole lot just from this equation. But it's 9 o'clock, and I know you guys are getting tired of hearing about this stuff. So let me finish up. Oh, by the way, on the quiz, when you get to this part of the quiz, I'm not going to ask anything about wavelength. I'm just telling you this for your own personal knowledge because I think it's interesting. I mean, this stuff you'll be responsible for, but like the wavelength, I mean, this I'm not going to ask about. This is more of an advanced topic or physics or something like that. So don't worry about being tested over this. But this kind of stuff you should be able to do. But you got to admit it's interesting. All right. If anybody misses this one, I'm going to stick my hand through the camera and pimp slap you. If you don't know what a pimp slap is, look it up in YouTube and you'll see it. All you got to do is look right here, right? Whatever that is, that's omega. Omega is 455, but don't forget your units. The unit for that is radians per second. And what would be interesting is, since we know the generators turn at 455 radians per second, it'll be interesting to convert that to revolutions per minute, RPMs. I got a better feeling for RPMs. So I'm not going to ask you to do that, but if you do this at home, I could ask you to do something like that. So we're all done except for the very last problem. And he said, what is that problem? It says, if the waveform is placed across a circuit consisting of a 100 ohm resistor, they want you to find the RMS current and an expression for the instantaneous current. Well, that sounds kind of hard. Actually, it's not. Let's see what he's talking about. What he's saying is, let's say you have a circuit. Now, we all know that for a resistor, I use this symbol. And for a voltage source, I can use this symbol. I can use this symbol. Or I can use this symbol. This right here is a battery. This right here is a cell. And this can be either or. In this class, I don't care. I mean, strictly speaking, there's a difference between a battery and cell. I'm not going to go into it, but I don't care which one of these you use. But these are all DC. In this class, how you represent a voltage source? Well, if it's DC, you can use one of these, but an AC voltage source looks like this. So that's the way I represent AC. And often they put the positive and negative there. You might wonder, well, why do I have positive and negative there if it alternates back and forth? But what we do in this class, as things are moving, we take a snapshot of it. So imagine I got the sine wave moving, I take a snapshot of it, and this is what I got, that polarity. It's going to either be like that or like that, but we typically show it like that. So if I have an AC waveform of 120 volts, I can write it like that. Now, so it says we have a AC circuit. So let me draw the circuit. I got the voltage source. By the way, don't confuse that with this. What's different between this and this? Anybody know what this is? I'm going to assume by your silence you don't. This right here is an AC source. It's a voltage source. This is a fuse. So just that without the circle is a fuse. If I put a circle around it, I guess it could still be a fuse. Sometimes I see them with circles, but don't confuse that with this. Anyway, let me get, I'm using up your time. So we got this. We got a resistor. They tell you the resistor is 100 ohms. But that voltage is at 167.5 sine 455t. That's my V. That's this. So given that, they say, all right, then let me know what I want the, what do I want? I want the RMS current, so I want IRMS, and I also want the expression or the equation that gives me the instantaneous value for I. So I guess the IRMS is the easiest to do. So let me see, make sure I read it right. If the waveform is placed across a 100 ohm resistor, find the RMS and find an expression for the instantaneous current. So that's this one. Well, this is easy right here because IRMS, all I got to do is take VRMS divided by R. So V over R is current. V peak over R would be I peak. V peak to peak over R would be I peak to peak. V average over R would be I average. They asked about RMS, so V RMS over R would be I RMS. So I forget what it was. What was our RMS voltage? How much was that? I erased it. What was it?
$118.4.
Divided by 100 ohms gives me 1.184, and that would be amps. So I'm going to say IRMS, and there's my value. So whatever my voltage value is, if I divide by resistance, my current will be in that same value, RMS, peak, so forth. What about this one? They asked about the expression for the instantaneous current. How would you do that? Well, that actually turns out to be really easy if you know what you're doing. So let me show you. You take, to get I of t, just take my V, this thing, and divide it by R. The instantaneous voltage over the instantaneous voltage over resistance gives you the instantaneous current, but I can do that with a whole expression. So what I can say is, since I know my voltage expression is this, I can take 167.5 sine 455t, and I can divide that whole thing by R, which is 100. You might say, well, how can you divide that whole expression by 100? Well, it's easy, because all you got to do is divide this part. Divide that part. So that gives you your expression. So if I take 167.5 over 100, I get 1.675 sine 455t, and now this becomes my expression for current, I of t. You tell me what time t to look at it, I'll tell you what the current is at that time. That's the expression for instantaneous current. Whew, that's a lot, and it is almost 9:10. So we went through a lot of material today, guys, but it's good stuff. Now we're starting to work with the math. This class has a lot of math in it, trig, algebra, physics, it's a lot of it, and don't make sure, because here's the bad thing about taking this class online, which you're not going to do probably next week. If not next week, definitely the week after, we'll meet face to face. But it's so easy to say, all right, you know what? I'm not even going to listen to him talk right now. I'll listen to the recording later. And before you know it, later becomes a week, you're 2 or 3 weeks behind, and it's impossible to get caught up. It's a lot of stuff in this course. So every week, whatever I put out there on Blackboard, go through all that material, all that work, and stay caught up. It's important. If not, I guarantee you, you'll get behind, you'll end up with a low grade, or end up taking the course over. So if you're already behind, you got enough time to turn the ship around and get caught up, but we just keep moving right along at the speed of light. We move really fast, and there's a lot of stuff. Anybody have any questions for me over anything we talked about? I I'm not done yet. I got a couple more things I want to say, but this is a good place to pause to see if, make sure everything's clear. Anybody have any questions for me over any of this stuff? Okay, well, I want to add one more thing to our model for the AC waveform. I want to add one more thing. And this is called phase angle. The phase angle. So that is the last piece. So I don't know when you guys in your algebra class, when you learn about equations, like let's say you have and I'll just try to explain it in a brief, just a few seconds here. If I have say I have some kind of graph, I can shift the graph. Let's say sometimes you'll say, all right, this right here is f of x. I can shift the graph up, I can shift the graph down. Like if I add a constant value to it, a number, and that'll shift the graph up c units. If I subtract a number from that, that'll shift the graph down c units. You might remember this in algebra, the curve shifting. The question is, what if instead of adding and subtracting a constant to the function, what if I went inside the function and added a number, or what if I went inside the function and subtracted the number? What would that do? Well, it turns out it wouldn't shift it up and down, but if you add it inside the function, it'll shift it from the left to the right. I don't know if you remember that or not, but I'm going to remind you. So what I'm going to do is on our function, which looks like this, V equals Vp sine omega t, right? And remember, omega equals 2 pi f. And also remember that f equals 1 over the period. So these three equations, because you can substitute this into there, and this into there, you can get whatever I ask you on the quiz or exam. Everything is done with those three equations. Remember these. But what I was going to say is, there's one more piece here. This is instantaneous voltage. This is peak voltage. That's angular velocity. The angular velocity of what? It's the angular velocity of the generator. And I can add plus or minus beta. And when I do that, I want to put this in parentheses. Okay, and what that beta is called the phase angle or the phase. So I can add or subtract, and this is in degrees. This is weird because this part right here, I told you that's always in radians, but this part right here is always in degrees. So it might look like this. I might give you script B is 100 sine 377 t minus 20 degrees. So that will be the waveform like that. And you know that that's the peak voltage or amplitude. That's the angular velocity. But this right here is the phase angle or the phase. This is in radians. The product of these is radians, but that's always in degrees. It's a weird way to show it, but it's actually kind of nice because here's what this does. Let me show you what this does. I'm going to erase this. If I have a function, I'll do it the math way. If I have this function like this, so that's the f of x I talked about. If I take that f of x and I take the x and I add a constant to it, what it will do is it'll take this whole wave and move it back that way, C units. If I subtract a number from it, it'll take that wave and push it this way, C units. So what I'm saying is, if I have this waveform right here, I have that waveform, and I draw it, here's what it'll look like. It's just a sine wave. That's what it looks like. I know the peak value is 100. Now, let's say I added this. I say it's going to be plus, I don't know, 90 degrees. Well, a plus sign, what it'll do is take this and it'll shift it back this way, 90 degrees. Now, I know 90 degrees. Let's put our degrees in here. This is 360. This right here is 180. This is 270. 90 is right here. This is 90. So by adding 90 degrees, it doesn't move it over this way. If that's a positive sign, it's going to pull it back over this way. So the wave is going to shift this way, 90 degrees. It's going to look like this. This point right here is here. It's going to shift over 90 degrees. If I had a minus 90 there, then this wave is going to shift this way. It'll move that way, which means the negative part is down here like that. So by adding a plus or minus angle here, if it's a plus, it's going to shift it to the left. If it's a minus, it's going to shift it to the right. That's called the phase angle or the phase. So the complete way of writing an AC waveform, if I want to be complete, will be what I said earlier. It's going to be script B, is VP, sine omega t plus or minus beta, instantaneous voltage, peak voltage, angular velocity, and then the phase shift, phase. Or phase angle. Whew. 9:18, 9:15 or something, and now we're finally through this stuff. And I still got, well, I had 10 people, now I'm down to 9, so you guys stuck with me. Let me close out this way. First, let's see. Let's look at just make sure we covered everything. So let's look at this. So I started.
Before you go, I got a question.
Yeah, go ahead.
Besides moving the wave right to left, what does the phase angle do?
Okay, by itself, nothing. Let me get off camera. Let me get off of that. So by itself, it doesn't do anything, right? But when we have phase angle, what we're usually we're concerned about how one waveform compares to something else. So here's what I mean. I might have, let me see how I can explain this without, because you're pushing me ahead to another topic, which I don't mind, but I'm trying to explain it with what you know so far. So what I'll do in here is I'll give you a problem like this. And I'll have some stuff over here. There's some more stuff here that we haven't talked about. All you know right now is resistors. There's other things that I can put in this box that are oppositions. I can't spell tonight. Opposition. Okay, so the only opposition you know right now is a resistor, but what I'm saying is there's other things we'll talk about. Maybe next week we talk about AC oppositions. I think it's next week. and you'll know what's in this box. But we gotta know where waves are with respect to each other. So that's kind of what the phase tells us. So if I have a resistor, here's what happens. If I have just a resistor in this box, then what I know is the voltage of this, let's call this the supply voltage. And the voltage across, let's say I got a bunch of resistors in here. Well, all those voltages across those resistors are what we call in phase, which means they zero at the same time. So I'll have the voltage across the resistor, maybe that's VR, they all happen at the same time. But the other elements, which is going to turn out being either a capacitor or inductor, it's going to cause the waveforms to shift either to the left or to the right. And sometimes it's important to know where those waveforms are with respect to each other. Now the problem is it's hard to see that with sine waves. Like if I show, say I put another element in here that causes the voltage across that element to shift over like that, it's hard to see it that way. So we're not going to draw it this way. We're going to draw it using phasors because it's much easier to see. I can represent a sine wave as a phasor. It's much easier to see a phasor like that and then one like that than it is if I draw it as a sine wave. So you kind of got me off guard because I'm trying to explain a topic, but you don't know enough yet for me to explain it. But I think you'll see where this comes in next week. I think next week the topic is AC oppositions, and that's where that comes in. You'll see how phase shifting works. So we'll just say that sometimes it's important to know where these waveforms are with respect to each other. This only tells us where this waveform is, but depending on what I put in the box, the voltages can go crazy. They can be anywhere. Sometimes we got to know where they are with respect to each other. So this by itself is not that important, but when I have other waveforms in there, this compared to where those other waveforms, that is important. So what I would say, I don't know who that was asked the question, just kind of take that for what it's worth, but then next week, you can ask me that again, or by then, I think your question will be answered. You'll see why that's important. Anybody else? All right, well, let me go through this, and then if you have more questions, I'll be happy to stick around. I just want to look at this real quick to make sure you have any questions, because if I make a quiz, it's based on this. So here's the topic sheet, and I think last week we talked about this. All of that should be clear. So we talked about Faraday's law, and we talked about the sideways force acting on the charge using the right-hand rule, and then we talked about basic generator construction, and I showed you a generator, and we used that video that you watched to explain generator action. So we went through all of that. What we did this week, we did this. We looked at all these terms. So you look on here from what I talked about today, you should be able to describe or understand all these terms here. I think you'll see that we covered all of that. And then down here, the AC model for a waveform, we did that. Well, that's just expressing a voltage or current waveform in this form right here. The only thing we didn't talk about was this idea of time domain and phasor domain. So it's pretty easy. I'm not going to talk about the phasor domain until next week, but time domain is just this. It's expressing, let me go off camera. Let me just show you. From your math class, you might remember from your math class, given this equation, a y equals 2x plus 1. Okay, so this right here is your independent variable. This right here is your dependent variable. You remember that from algebra. Well, the number that you're allowed to put in there, the values of x, whatever value that is, the value you can put in there for x, the allowed values for x is called your domain. And depending on what you put in there, depending on what's in your domain, when you put it in there and calculate y, the values you get for y is called your range, using x's and y's. Well, in electrical engineering, we don't use x and y, we use b and t. So instead of our domain being x, our domain is t. So when you write an AC waveform like this, They call it time domain because our domain is T. That's what that means on that paper. What I didn't talk about, the only thing I didn't talk about tonight, and I'm not going to do it tonight, I'll do it next week, is there's time domain, which is just anytime you have a sine or cosine using current or voltage, that's time domain. There's another way to write this, which is what we'll do next week, called phasor domain. You know what a phasor is. There's a way to write voltages and current using phasors, and that's called phasor domain. So I'll explain. You should know what time domain is, but I will explain phasor domain next time we get together. Let me go back to that sheet. Hold on just a second, just to make sure. So you expect you to be able to calculate anything on this sheet right here. Like if I give you a quiz, you should be able to do anything here except for I wouldn't ask about this one, and I wouldn't have you do this one. Those two you don't have to worry about, but anything else on that sheet, if I came in here and put a problem on the board and it's related to 1 through 7 or 9, I would expect you to be able to do it. Okay, so anybody have any questions over any of those problems? That's what we just did on the board. All right, well, let's look at this one. We didn't look at this sheet yet. Get a chance to read this sheet. This says Heinrich. This is the guy I told you was a Heinrich Hertz. He's a physicist, and he's the one that has the Hertz frequency named after him. But you should be able to answer. We don't have to do it now, but from this graph, you should be able to answer these questions. I don't really want to do it now. Maybe I'll warm up with this next time. But just from the graph, you can do it analytically, right? If I put the numbers on the board, but can you answer these questions from the graph? And you should be able to do that. So here, what's the peak voltage? What is the peak value? I don't know what it is, but I know it's right here. That's the peak value. What's the instantaneous value at 0.3 seconds? Well, we just kind of got to estimate. If this is 2.2 and that's 0.4, 0.3 is like right in the middle, and so that would be the negative peak voltage over here. So that kind of stuff you should be able to do. So be able to go through this. And if I think about it, I'll run through this sheet at the beginning of the next class as a warm-up. Okay? So look at that. We'll talk about it if I remember. And the only other thing I'm going to do is let's look at the homework real quick. So now that I'm done with this, you should be able to do homework 1. And hopefully you looked at homework 1, but if you didn't, it's on Blackboard. It's been on Blackboard. Here's homework 1. So I expect you to have that done next week. And if you look at these problems, they should look familiar to you now after what we talked about today. So you should be able to do all of these problems based on what we talked about for homework 1. Okay? So I think that's it. That's all I have. Does anybody have any questions for me?
Yes. I wanted to clarify, so on the phase angle, when it's positive, it moves sinusoidal wave to the left, and when it's negative, it goes to the right?
That's correct.
Okay.
When it's positive, you shift to the left. When it's negative, it shifts to the right. So it's the opposite of the way you would think. That's right.
Okay.
Anybody else?
And can I resubmit my Tesla paper, because I sent it in with the Word document and not a PDF?
Oh, you're okay. I can open it up. It's just, I think you'll be okay. If there's a problem, I'll have you resubmit it. But I know PDFs work no matter what computer I'm on. But I think it'll open all right. If I see that you submitted it and I can't open it, I'll get a hold to you and tell you to resubmit it. But just in general, I like PDFs, but you'll be okay.
Thank you.
You're welcome. You had very good questions today, too, by the way, so thank you. Anybody else have any questions?
Yeah, for next week, you say homework 1, and you're going to post a quiz on Saturday. That will be due for next week, right?
So what I'm gonna do over the weekend, I'm gonna post the quiz will be due over the weekend. I'll probably won't get to it until tomorrow or Saturday, but I'll for the weekend, you'll have, here's what you should do. Make sure you're working on lab 1, because lab 1 is going to take you a couple weeks. So hopefully you're not just starting on it. But if you are, make sure you do that, because lab 1 is going to be important for what we do, I think, next week. I think next week. But do lab 1. I'm going to give you another lab that you can do at home. So you did lab 1 already. You're working on lab 1. I'll give you another lab you can do at home. So you'll have that to do over the weekend. You'll have a quiz to do. You'll have another lab to do, and then you'll have homework 1. You should be able to do homework 1 now. Right? So you'll have all that to do over the weekend. Now, I'm not going to collect it over the weekend. The only thing I'm going to collect or have you turn in over the weekend will be the lab and, I don't know, possibly homework 1. I might want to give you more time on homework 1. So we'll say the lab will be due over the weekend and the quiz. Homework 1, when I say the lab, I don't mean lab 1. I mean lab 1 I'm going to give you a couple weeks to do. But the lab I assign over the weekend will be due maybe Sunday at midnight. And then that'll be due, and I forgot what else I said. So I'll make sure it's clear on Blackboard, okay? I'll make sure everything's clear. Right now I'm getting tired and my mind is not working right. I can't think about what I'm saying. So what's due, I'll put, it'll be clear what's due. Definitely there'll be a new lab and the quiz. Those are the 2 things that's due. There'll be a new quiz I post over the weekend and the new lab I post. We'll call it lab 2 for now. It'll be due over the weekend. You'll be able to upload it to Blackboard. Anybody else?
And we read chapter 11, sections 1 through 7. Did you have do we need to do the next chapter reading and understanding?
Whatever's on the syllabus, I will follow that. Yeah, just look at that syllabus as a schedule of readings there. Just look at that and follow that. The guys, to me, I don't know how you do it. This stuff, I'm going to be honest. When I was in college, this is one of the hardest courses I took. Now, mine was all calculus stuff and all that, but still, even here, it's not an easy course. The concepts are really abstract. So the best way to get a grip on what we're doing, try to read the material before you come to class, because then you got an idea what I'm going to talk about. If you read it and then I say it, so you read it and then you hear me talk about it, and then you try to do the homework. And for the people that really want to get an A, you have something I didn't have when I was in college. I didn't have YouTube. But now you can go to anybody's YouTube channel and actually see a visual of what we're talking about. So between reading it, me working problems and talking about it, and you looking on the computer, you should be able to really get your mind wrapped around what I'm talking about. So I highly recommend trying, when you can. I know everybody's busy. Ideally, try to read before I talk about it. That way, number one, you kind of got an idea what I'm going to talk about. You heard it from a different voice. The author of your book is a different voice than mine. So hearing it from different voices will definitely help you. So I know you didn't ask for all that, but yeah, read the next chapter if you can. Try to do it before we talk about it. But even if you don't get behind in the reading, because there's things in the book that I'm not going to talk about that I still expect you to know. So make sure you read.
So chapter 15 for next week then.
Whatever's on the syllabus. I don't have it in front of me. I'm a week behind because this first chapter, it always takes long for me to go through the material. But follow the syllabus. So whatever, I don't know what the first chapter in there is. That first chapter of reading was week 1. You should have already read that. So whatever the next chapter is, I guess for week 2, that's what we're going to talk about next week. Anybody else? Going once, going twice. All right, guys, I'm about to go home. Stay safe. If you have any other questions, please feel free to send me a text. And I will see you guys next Thursday. Stay safe.